the hydrogen flow rate is stabilizing exactly as projected.
Pipe dream. Pirate first.
Stoff. Unter Verwendung von hydrostatischem Druck.
Pipe Dream Part 10. The Deep Intelligence. MXDM, aka Pirate 1 VJ Cinemiex. July 21st, 2026. Chapter 1. The Chemostat. The anoxic zone is where the cenote stops being a human story. The freshwater zone is the civilization's home. The thermal stability, the optical clarity, the biological community managed toward the ecological richness that the living maintenance crew sustains and the visitor experience presents. The halocline is the transition, the geological boundary where the fresh and the salt and the chemistry meet in the optical dissolution that the scaphander participant experiences as the most visually distinctive event in the freshwater zone's full sensory range. The saltwater zone is increasingly foreign, the ALON panels, the H2S detection concentrations, the biological community's composition shifting toward the extremophile taxonomy that the surface world's biology textbooks address in the chapters whose titles begin with life at extremes. The anoxic zone is where the extremes become the norm. Below the depth at which the dissolved oxygen reaches zero, the boundary that the oxygen sensor network monitors at a parts per million resolution and that the biological management protocol treats as the inhabited installation's operational floor, the hydrogen sulfide that the sulfate-reducing bacteria's anaerobic metabolism produces becomes the dominant dissolved chemical species in the water column. The H2S concentration increases with depth below the anoxic boundary as the sulfate-reducing metabolism's output accumulates in the water column that the dissolved oxygen's absence has deprived of the oxidizing capacity that would otherwise consume the H2S as it is produced. The anoxic zone is lethal to every biological system in the inhabited installation above it. The Bodo population's behavioral deterrent array marks the halocline boundary as the behavioral range's floor. The crystal tube network's deepest gallery rings are rated for the H2S concentrations detectable at the halocline's lower boundary, but not for the full anoxic zone's concentrations. And the scaphander's rated operating depth is the freshwater zone's full extent to the halocline boundary, not beyond it. The anoxic zone is not the installation's floor in the operational sense. It is the installation's deepest industrial production environment, the geological context in which the chemostat operates as the civilization's most productive and most specific economic asset, the biological metabolism whose industrial output the surface world cannot replicate by any alternative production pathway because the anoxic zone's specific biological community, its specific geological chemistry, and its specific thermodynamic conditions are the chemostat's production prerequisites, rather than its production inputs. The chemostat is where the formation's 66 million year investment in biological specificity becomes the civilization's most durable competitive advantage. What the chemostat is. The chemostat in the surface world's biological laboratory is a continuous culture fermentation vessel whose operating principle is the steady-state maintenance of the biological community's growth conditions, the continuous supply of growth-limiting nutrient at the controlled rate that maintains the biological community's population density at the steady-state level, where the growth rate equals the dilution rate, producing continuous biological output at the steady-state population's metabolic rate. The laboratory chemostat's value is the reproducibility it produces. The steady-state conditions generate the same biological output continuously, allowing the experimenter to make controlled observations of the biological community's response to specific experimental perturbations without the confounding variables that the batch culture's exponential growth and stationary phase transitions introduce. The chemostat is the laboratory's controlled environment for studying continuous biological metabolism. The anoxic zone's chemostat is the geological formation's version of the laboratory's controlled environment, not the experimenter's construction of controlled conditions in a vessel whose parameters the experimenter specifies, but the formation's geological construction of the specific thermodynamic and chemical conditions, the temperature, the pressure, the dissolved sulfate concentration, the absence of dissolved oxygen, the specific mineral substrate composition that the anoxic zones, extremophile biological community requires for the metabolic activity that the chemostat's industrial output depends on. The geological construction is 66 million years old. The formation built the specific conditions before the civilization arrived. The civilization's Chemostat installation did not create the anoxic zone's conditions. It created the infrastructure that accesses the conditions the formation already provided and operates the biological community management that maintains the conditions within the narrow range that the extremophile community's metabolic productivity optimizes at. The chemostat's industrial metabolism is the extremophile community's collective biochemistry at the anoxic zone's specific conditions. The sulfate-reducing bacteria's reduction of dissolved sulfate to dissolved sulfide as the primary energy-generating reaction, coupled to the sulfur-oxidizing bacteria's oxidation of the dissolved sulfide to elemental sulfur at the geological substrate's mineral interface, producing the elemental sulfur that the chemostat's mineral harvest program collects as the first of the anoxic zone's industrial outputs. The elemental sulfur production is the chemostat's most volumetrically significant output and the most immediately commercially accessible. Elemental sulfur is a global commodity whose applications in fertilizer production, industrial chemistry, and materials science produce a commodity market whose pricing the chemostat's production cost significantly undercuts. The Chemostat produces elemental sulfur from the dissolved sulfate in the cenote's saltwater column using the extremophile biological community's metabolic machinery at the energy cost of maintaining the chemostat's operational infrastructure rather than the energy cost of the clause process or the fresh process that the surface world's sulfur production requires. The energy cost differential is the chemostat's primary economic advantage over the surface world's sulfur production. The chemostat's biological metabolism captures the free energy that the dissolved sulfate's reduction releases as the biochemical reaction's driving force, rather than consuming external energy as the thermodynamic input that the surface world's sulfur recovery processes require. The biological metabolism is the energy harvesting mechanism. The elemental sulfur is the energy harvest product. The three-gallery installation. The chemostat's physical infrastructure organizes the anoxic zone's biological metabolism management into three-gallery installations whose functions reflect the biological community's distinct metabolic zones within the anoxic column's vertical extent. The primary gallery is at the anoxic boundary's immediate vicinity, the depth range where the dissolved oxygens transition to zero and the H2S's first appearance produce the chemocline, the chemical boundary layer, where the most metabolically diverse extremophile community exists in the steep chemical gradient between the fully oxic conditions above and the fully anoxic conditions below. The primary gallery's biological management maintains the chemocline's chemistry within the gradient range that supports the maximum taxonomic diversity and the maximum combined metabolic rate of the chemocline's biological community. The chemocline's biological community is the chemostat's most scientifically significant installation component. The gradient between oxygen and sulfide at the chemocline supports the metabolic coupling that the most energy-productive biological systems require. The electron transport chains whose efficiency depends on the electrochemical potential difference between the electron donor and the electron acceptor. The chemocline's oxygen sulfide gradient is the largest electrochemical potential difference available in the cenote's natural chemistry, and the biological community that the gradient supports includes the highest specific activity metabolic systems in the anoxic zone's full biological inventory. The secondary gallery is at the mid-anoxic depth, the range where the dissolved oxygen is fully absent and the H2S concentration has reached the intermediate level that the sulfate-reducing bacteria's metabolic rate produces at the sulfate depletion depth. The secondary gallery's biological management maintains the sulfate supply, the dissolved sulfate from the saltwater column's mineral loading, within the concentration range that the sulfate-reducing bacteria's growth-limiting nutrient model specifies as the optimal growth rate's production condition. The tertiary gallery is at the deep anoxic zone's mineral substrate interface, the depth range where the water column meets the geological substrate's mineral surface and the lithotropic biological community, the organisms whose energy metabolism is driven by the mineral substrate's chemical oxidation, achieves the highest surface area-specific metabolic rate that the substrate contact provides. The tertiary gallery's biological management maintains the mineral substrate surface chemistry within the range that the lithotropic community's attachment biology and the mineral dissolution reactions kinetics together specify as the optimal production condition. The three galleries' combined biological management produces the integrated anoxic metabolism that the chemostat's industrial output requires. The primary gallery's chemocline diversity generates the metabolic coupling that the electrochemical harvest exploits. The secondary gallery's sulfate-reducing metabolism produces the elemental sulfur that the mineral harvest collects. And the tertiary gallery's lithotropic metabolism produces the mineral dissolution outputs, the dissolved metals, the trace minerals, the rare earth elements that the chemostat's specialty chemical production program processes and concentrates. The biological community's geological heritage. The anoxic zone's extremophile biological community is not the founding biologist's deployment package. It is the formation's 66 million year resident, the community that survived the geological timescale's selective pressure in the specific anoxic conditions that the Chicxulub impacts fracture geology and the Yucatan's hydrogeological gradient together produced in the cenote's deepest zone. The community's geological heritage is its most commercially significant property. The 66 million years of selection in the specific anoxic conditions have produced secondary metabolite production pathways whose specific biochemical products the surface world's pharmaceutical development has not encountered in any other biological source. The secondary metabolite's novelty is the direct product of the biological isolation that the cenote's geological closure imposed on the anoxic zone's biological community across the evolutionary timescale. The community's genetic diversity was shaped by the specific chemical and thermodynamic conditions of the Yucatan's anoxic cenote environment rather than by the genetic exchange with the broader biosphere that the connected ocean's biological community experiences. The genetic isolation's product is the biochemical novelty, the enzyme variants, the biosynthetic pathways, the structural metabolite architectures that the 66 million year selection produced in the specific anoxic conditions are the biochemical novelties that the pharmaceutical development pipeline identifies as the highest value outputs of the chemostat's biological community management. The pharmaceutical development pipeline's assessment is not the Research Commons' primary driver. The Research Commons publication series treats the anoxic zone's biology as the scientific investigation's primary motivation, and the pharmaceutical application is the scientific investigation's commercially significant consequence rather than the research program's primary purpose. But the pharmaceutical consequence's commercial significance is real, and the founding charter's commons ownership principles' intellectual commons provisions ensure that the biochemical novelty's pharmaceutical development proceeds through the research commons licensing framework rather than the proprietary ownership that a pharmaceutical company's direct access to the anoxic biological community would impose. The community's pharmaceutical output is the commons. The commons licensing terms are the scientific value maximization standard. The scientific value maximization produces the pharmaceutical development that the commons access enables across the full research community's engagement with the biochemical novelty. The pharmaceutical development's commercial value is captured in the licensing income that the commons governance protocol distributes to the expansion reserve rather than to the proprietary portfolio that the individual pharmaceutical company's exclusivity claim would concentrate. The thermal loops. The chemostat's most thermodynamically significant physical provision is the dual thermal loop, the two separate heat exchange circuits that the anoxic zone's geological thermal conditions and the chemostat's biological metabolism together make available as thermal energy sources for the installation's energy accounting. The first thermal loop is the geothermal. The anoxic zone's geological substrate maintains a temperature that exceeds the saltwater column's water temperature by the geothermal gradient that the crustal heat flux produces at the anoxic zone's depth. The geothermal excess temperature is modest, a few degrees Celsius above the water column's ambient, but the thermal mass of the geological substrate and the steady-state heat flux that the crustal origin produces make the geothermal thermal loop a continuous low-grade thermal energy source whose consistency across the design life the geological thermal model confirms as stable. The geothermal thermal loop's energy extraction uses the closed-circuit heat exchanger whose working fluid circulates between the geological substrate's heat exchange panels, the ALON panels mounted in contact with the geological substrate at the tertiary gallery's installation depth. and the thermal management applications in the higher installation levels that require the low-grade thermal energy the geothermal source provides. The working fluid absorbs the geothermal thermal energy at the geological substrate surface, circulates to the thermal management application, releases the thermal energy at the application's operating temperature, and returns to the geological substrate surface for the next thermal absorption cycle. The second thermal loop is the metabolic. The anoxic zone's biological communities, metabolic activity, the sulfate reduction, the chemolithotrophic metabolism, the mineral dissolution reactions, generates biochemical reaction heat as the thermodynamic consequence of the exothermic reaction's energy balance. The biochemical reaction heat is released into the water column at the biological community's metabolic locations and is available for extraction through the metabolic thermal loops heat exchanger panels whose positioning within the biological community's metabolic zones captures the reaction heat at the proximity that the heat exchanger's thermal contact requires. The metabolic thermal loop's energy extraction is more spatially distributed than the geothermal thermal loop's concentrated geological substrate interface. The biological community's metabolic zones are distributed across the three galleries' depth extent rather than concentrated at a single geological substrate surface. The metabolic heat exchanger's spatial distribution reflects the biological community's spatial distribution. Panels positioned within the primary gallery's chemocline zone, the secondary gallery's sulfate-reducing zone, and the tertiary gallery's lithotropic zone, each capturing the reaction heat that the biological community at that depth produces. The dual thermal loop's combined output is the chemostat's thermal energy production, not a large fraction of the installation's total thermal energy budget, but a consistent, passive, maintenance-free thermal contribution that the energy accounting's thermal allocation includes as the installation's geological and biological energy harvest. The passive thermal contribution reduces the thermal energy that the methane digester's combustion and the formation's passive thermal stability must provide from the other thermal energy sources, releasing the methane's thermal output for the higher temperature applications that the geothermal and metabolic thermal loop's low-grade output cannot serve. The membrane reactor. The membrane reactor is the chemostat's most technically sophisticated process component and the one whose output has the highest energy density per unit volume in the installation's full energy production inventory, the hydrogen production system that the anoxic zone's biochemical conditions make possible at the membrane reactor's specific operating depth. The hydrogen production pathway in the anoxic zone's chemistry is the hydrogenase enzyme's catalysis of the proton reduction reaction. The extremophile community's hydrogenase-expressing members catalyze the reduction of dissolved protons to molecular hydrogen gas using the reduced electron carriers that the sulfate reduction metabolism generates as the biochemical couplings product. The hydrogen production rate is proportional to the sulfate reduction rate, the same biological community's metabolic activity that produces the elemental sulfur through the mineral harvest's collection pathway simultaneously produces the dissolved hydrogen through the hydrogenase enzyme's catalytic pathway. The membrane reactor captures the dissolved hydrogen by the continuous permeation of the dissolved gas through the membrane's selective gas transfer material, a palladium alloy membrane whose hydrogen permeability significantly exceeds the permeability of the other dissolved gas species in the anoxic water column. The dissolved hydrogen diffuses through the palladium membrane under the chemical potential gradient that the membrane reactor's sweep gas flow maintains on the membrane's non-aqueous side, producing the continuous hydrogen flux whose accumulation the compressed storage cylinder collects and whose distribution the hydrogen management system supplies to the fuel cell stack as the DC bus's primary electrical generation input. The fuel cell stack's hydrogen oxidation produces the electrical current that the DC bus delivers to the installation's electrical systems, the coordinating system's compute infrastructure, the light relays diode arrays, the maglev propulsion's electromagnetic infrastructure, and the atmospheric management's active components. The fuel cell's electrical output supplements the streaming potential harvest generation, the two independent electrical generation sources whose combined output the DC bus distributes across the installation's electrical load provides the redundancy that the blackout protocol's analysis identified as the streaming potential harvest alone cannot guarantee. The fuel cell's electrical output is not the installation's largest electrical generation source. The streaming potential harvest's continuous generation from the underground river's flow produces the baseline electrical supply, whose reliable output the fuel cell supplements rather than replaces. The fuel cell's significance is the fuel cell's fuel source. The hydrogen that the anoxic zone's extremophile biological community produces through the hydrogenase enzyme's catalytic pathway is the fuel that the membrane reactor collects from the dissolved chemistry that the formation's 66-million-year-old biology produces without any external energy input. The hydrogen is the biological metabolism's product. The metabolism is the geological chemistry's product. The geological chemistry is the formation's product. The formation is 66 million years old. The fuel cell is using 66 million years of geological investment as the electrical generation's fuel source. The hydrostatic compression credit. The anoxic zone's operational depth produces a thermodynamic resource that the surface world's industrial chemistry would pay significant energy costs to access. The hydrostatic pressure at the chemostat's operating depth is approximately 2 to 3 atmospheres above the surface pressure, depending on the specific gallery's installation depth within the anoxic zone's extent. The hydrostatic compression credit is the chemostat's thermodynamic bookkeeping term for the energy equivalent value of the elevated pressure that the geological depth provides for the chemostat's process conditions. Every chemical process that benefits from elevated pressure, the gas dissolution reactions that dissolve more product at higher pressure, the membrane reactor's hydrogen permeation that the partial pressure gradient drives, the industrial chemistry's reaction kinetics that the collision frequency's pressure dependence accelerates, is operating at the elevated pressure that the geological depth provides without any pumping energy expenditure. The pumping energy that the surface world's industrial chemistry must expend to achieve equivalent operating pressures is the hydrostatic compression credit's economic comparison. The chemostat's processes operating at 2 to 3 atmospheres above the surface pressure spend zero pumping energy on the pressure elevation, because the geological depth provides the pressure as a passive thermodynamic consequence of the water column above the operating depth. The hydrostatic compression credit is the thermodynamic expression of the aquaforming doctrine's economic argument. The formation's geological conditions provide the thermodynamic resources that the industrial process requires at no energy cost, because the formation's conditions are the process conditions rather than the conditions that the process must manufacture. The surface world's industrial chemistry manufactures the elevated pressure that the chemostat accesses passively. The manufacturing's energy cost is the hydrostatic compression credit's economic value, the energy that the chemostat saves by being inside the formation rather than replicating the formation's conditions in a surface world industrial facility. The DC bus. The DC bus is the chemostat's electrical integration point, the common direct current electrical bus that receives electrical generation from the streaming potential harvest's electrochemical cells, the fuel cell stack's hydrogen oxidation, and the piezoelectric sensor network's mechanical vibration harvest, and distributes the combined electrical output to the installation's full electrical load across the crystal tube network's depth extent. The DC bus architecture is the chemostat's electrical management principle applied to the full installation's electrical system, not separate AC electrical systems for each generation source, with a frequency synchronization infrastructure that the AC bus's parallel generation requires, but a single DC bus whose voltage the generation sources and the distribution loads share without the frequency management that the AC system imposes. The DC bus's simplicity is the chemostat's electrical management contribution to the installation's operational overhead reduction. One bus, one voltage reference, multiple sources, multiple loads, no synchronization infrastructure. The DC bus's voltage level is the compromise between the generation source's output characteristics and the distribution load's input requirements. The streaming potential harvest's electrochemical cells produce a low voltage, high current output whose parallel aggregation builds the bus voltage. The fuel cell stack produces a variable voltage output whose DC-DC converter steps up to the bus voltage. And the distribution loads, the light relay's LED drivers, the maglev propulsion's power. Electronics, the coordinating system's power supplies, require the regulated voltages that the bus-connected DC-DC converters produce by stepping the bus voltage down to the load's specific requirement. The DC bus architecture's most important operational property is its natural energy sharing. When any generation source's output increases, the streaming potential harvest's output increases with the underground river's flow velocity. When the wet season's water table rise accelerates the hydraulic gradient, the increased output raises the bus voltage, which the other generation sources and the load's connected electronics respond to automatically. The energy sharing is not the result of a control system's coordination. It is the consequence of connecting multiple sources and multiple loads to the same DC bus whose voltage the electrical physics mediates as the shared state variable. The DC bus is the electrical equivalent of the ecological commons, the shared resource infrastructure whose management the physics coordinates rather than the control system instructs. The generation sources contribute to the bus. The loads draw from the bus. The bus voltage is the common state variable that reflects the balance between generation and consumption at each moment. The hybrid classical quantum compute mesh. The coordinating system's computational architecture was introduced in Part 2 and referenced throughout the preceding parts as the dual-mode compute infrastructure whose classical neural compute layer handles the high-volume, low-coherence logistics and whose quantum interference nodes handle the long-horizon pattern recognition. The Chemostat's installation is the deep intelligence infrastructure's physical anchor, the compute mesh whose three-gallery installation provides the physical depth separation that the quantum interference nodes' operational requirements demand. The quantum interference nodes require environmental isolation at a level of precision that the surface world's quantum compute facilities achieve through elaborate cryogenic infrastructure. The dilution refrigerators, the magnetic shielding arrays, and the vibration isolation platforms that the quantum coherence's sensitivity to the decoherent sources that the thermal environment, the magnetic field, and the mechanical vibration impose. The surface world's quantum compute facilities spend significant capital and operational energy on the environmental isolation that the quantum coherence requires. The anoxic zone's deep gallery provides a different isolation environment. The thermal stability that the geological depth's thermal mass produces is not the millikelvin cryogenic temperature that the superconducting qubit technology requires, but it is the parts per million level temperature stability that the photonic qubit technology's operating specification permits. The magnetic isolation that the limestone's diamagnetic properties provide is not the superconducting magnetic shielding that the flux-sensitive qubit requires, but it is the reduction of the surface world's electromagnetic interference that the deep gallery's distance from the electromagnetic noise sources provides. The photonic qubit technology's adoption in the Chemostat's quantum compute nodes is the Chemostat's quantum compute specification's most distinctive departure from the surface world's quantum compute industry's dominant superconducting qubit approach. The photonic qubit's operating temperature is not the millikelvin cryogenic temperature, but the room temperature thermal environment that the deep gallery's thermal stability maintains. The photonic qubit's operating environment is the deep gallery's conditions rather than the cryogenic facility's construction. The hybrid classical quantum compute mesh's division of computational function is the coordinating system's most important architectural provision. The classical neural compute layer handles the real-time monitoring data processing, the production planning, the biological management protocols, routine management decisions, and the visitor experiences AR management. The high-volume tasks whose correct real-time execution the classical compute architecture optimizes for speed and throughput. The quantum interference nodes handle the long-horizon pattern recognition, the formation model's deep geological structure analysis, the ecological succession model's multi-century trajectory projection, the legal strategy's geopolitical pattern recognition, and the governance record's generational pattern analysis, whose solution the classical compute architecture cannot approach within the solution quality and the temporal depth that the coordinating system's intelligence function requires. The quantum interference node's long-horizon pattern recognition is the deep intelligence's most direct contribution to the civilization's governance. The patterns that the quantum computation identifies in the formation's geological data, the ecological succession's historical trajectory, and the legal strategy's political context are the intelligence inputs that the terraform operator's professional judgment interprets and the Redeemer framework's governance decisions incorporate as the formation's long-horizon self-communication with the civilization's institutional intelligence. The formation communicates at the geological timescale. The quantum compute mesh listens at the geological timescale's pattern resolution. The civilization governs at the response timescale that the pattern recognition's intelligence enables. The chemostat and the civilizational argument. The chemostat is the civilizational argument's most economically specific expression, the industrial production that the formation's specific geological conditions make uniquely possible, organized through the biological community's metabolic intelligence that 66 million years of selection produced, and extracted through the engineering infrastructure that conforms to the formation's conditions rather than requiring the formation's conditions to conform to the infrastructure. The surface world's industrial chemistry would produce the chemostat's outputs, the elemental sulfur, the pharmaceutical secondary metabolites, the specialty minerals, the hydrogen through energy-intensive processes that manufacture the specific thermodynamic and chemical conditions the chemostat accesses passively from the formation's geology. The manufacturing's energy cost is the surface world's industrial chemistry's primary operational expense. The chemostat's passive access to the formation's geological conditions is the economic argument's quantitative expression, the hydrostatic compression credit, the geothermal thermal loop, the metabolic thermal loop, the streaming potential harvest's continuous electrical generation, and the membrane reactor's biological hydrogen production together constitute the energy budget whose zero-energy components are the formation's geological gift and whose minimal energy components are the biological management's operational overhead. The chemostat produces industrial output from geological conditions that the formation provides and biological metabolism that 66 million years of selection equipped. The civilization maintains the conditions and manages the metabolism. The industrial output is the collaboration's product. This is the aquaforming doctrine at its most economically specific, not the philosophical commitment to inhabiting without exploiting, not the aesthetic commitment to the civilization's invisible architecture, not the governance commitment to the commons ownership principles commons management. The specific, quantifiable economic outcome of building inside the formation rather than replicating the formation's conditions outside it. The chemostat's industrial output whose production cost is the formation's geological intelligence maintained at the biological management protocol's operational overhead, rather than the surface world's industrial chemistry's thermodynamic manufacturing of conditions that the formation provides for free. The formation is not free. The civilization paid 66 million years of geological time to have the conditions ready. The civilization arrived and found the payment complete. The chemostat is the receipt. Cross-references. Part 2, CH2, Engineering Invisible Architecture. Part 3, CH1, Rivers Beneath the Jungle. Part 5, CH6, Ecology as Infrastructure. Part 7, CH3, Compartmentalized Cities. Part 8, Section B, CH8, From Waste to Wealth. Part 10, CH2, Electrochemical Harvest. Part 10, CH3, the compute mesh. Part 10, CH4, the thermal architecture. Part 10, CH5, the mineral harvest. Part 10, CH6, ASI as co-creating partner. Part 11, CH1, living under pressure. For Chemostat 3 gallery installation specification and biological community management protocol, see Appendix F, Biological Operations Manual. For membrane reactor palladium alloy membrane specification and hydrogen collection protocol, see Appendix B, Power Architecture and DC Bus. For dual thermal loop heat exchanger specification and thermal management application allocation, see Appendix B, Power Architecture and DC Bus. For DC Bus architecture specification and generation source integration protocol, see Appendix B, Power Architecture and DC Bus. For hybrid classical quantum compute mesh photonic qubit operating specification and deep gallery environmental isolation assessment, see Appendix G, Formation Intelligence Record. Pipe Dream. Part 10, The Deep Intelligence. Chapter 2, Electrochemical Harvest. Electricity is the surface world's most invisible infrastructure. The coal mine is visible, the shaft head, the rail cars, the coal dust that covers everything within its geographic radius. The natural gas pipeline is visible, the right-of-way, the compressor stations, the metering infrastructure. The wind turbine is visible to the extent that the surface world's aesthetic debates have made it a recurring landscape controversy. But the electricity that all of these produce is invisible at every point in the transmission and distribution network, from the generation source to the socket, the wire, the transformer, the distribution line. None of these reveal what is moving through them to any sensory system the unaided human body possesses. The invisibility is the energy system's most governance significant property. The energy system that the user cannot see is the energy system that the user cannot monitor, cannot verify, and cannot trace from consumption back to consequence. The electricity in the socket has no origin story that the socket reveals. The kilowatt-hour consumed is disconnected from the coal burned, the watershed flooded, the community displaced, or the atmosphere loaded that produced it. The invisibility is not accidental. It is the transmission system's physical property applied to a political consequence. The energy system whose consequence is invisible at the point of consumption is the energy system that the consumer cannot be accountable for. Pipe Dream's electrochemical harvest is not invisible at any point in the production chain. The streaming potential harvest's production mechanism is the underground river's physical flow through the passage network, the water that the surface world above can observe entering the aquifer through the seasonal rainfall and that the acoustic monitoring network can trace through the passage geometry from the recharge zone's surface infiltration to the electrochemical cell's production interface. The fuel cell stack's hydrogen production is the membrane reactor's biological collection of what the anoxic zone's biological community produces as the metabolic output of the chemistry that the formation's geological 66 million year history provided. The piezoelectric sensor network's mechanical vibration harvest is the structural acoustic activity that the geological formation produces and that the civilization monitors as the safety architecture's primary geological intelligence source. Every electrical generation pathway in Pipe Dream's energy system is traceable to its geological, biological, and hydrological origins because every generation pathway is the formation's own physical processes organized for the civilization's energy access, rather than the surface world's energy infrastructure imposed on the formation's conditions. The energy is visible at its source because the source is the formation, the geological, biological, and hydrological reality that the coordinating system monitors continuously and that the Terraform operator's morning review confirms at every management interval. The streaming potential harvest. The streaming potential is the electrokinetic phenomenon that the surface world's geophysics uses as the primary diagnostic signal for understanding the flow of groundwater through porous geological media. When water flows through a porous or fractured geological medium, the water carries a charge imbalance at the water-mineral interface. The electrical double layer that the surface chemistry of minerals in contact with water produces, and the flow of this charge imbalance along the flow direction produces a streaming potential whose magnitude is proportional to the flow velocity and the water's electrochemical properties at the mineral interface. The streaming potential is a diagnostic tool for the surface world's hydrologists. The measurement of the streaming potential at 2 points in the geological medium tells the hydrologist about the flow velocity and direction between the measurement points, from which the hydraulic conductivity and the flow path geometry can be inferred. The surface world uses the streaming potential's energy as a measurement signal, a millivolt to volt scale voltage whose information content is the geological flow monitoring's value. Pipe Dream's streaming potential harvest uses the streaming potential's energy as a generation source rather than as a measurement signal. The electrochemical cells installed at the crystal tube network's passage walls capture the streaming potential's electrical energy as the underground rivers flow through the passage network produces it continuously, converting the flow-driven charge separation at the mineral water interface into the electrical current that the DC bus receives as the continuous baseline generation that the passage network's full hydrological extent provides. The streaming potential harvest's physical principle is the reverse of the electroosmotic flow that the surface world's microfluidics technology uses to pump fluids through channels by applying an electric field. The electroosmotic flow uses electrical energy to drive fluid flow through the mineral water interface's double layer. The streaming potential harvest uses fluid flow to generate electrical energy from the same double layer's flow-driven charge separation. The physics is the same. The electrical double layer's interaction with the flow field, with the direction of energy conversion reversed. The electroosmotic pump consumes electrical energy to produce mechanical work. The streaming potential cell produces electrical energy from the mechanical work that the hydraulic gradient provides. The hydraulic gradient is the underground river's energy source. The difference in the water table's elevation between the inland recharge zone and the coastal discharge zone drives the water through the limestone's passage network at the flow velocity that the hydraulic conductivity and the hydraulic gradient together determine. The hydraulic gradient is maintained by the regional rainfall's recharge of the inland water table, a continuous process that the surface world's hydrological cycle maintains through the evaporation, precipitation, and infiltration sequence that the regional climate produces. The streaming potential harvest's energy source is ultimately the solar energy that the regional hydrological cycle's evaporation requires. The solar radiation that evaporates the water that eventually precipitates and infiltrates and recharges the water table that drives the underground flow that generates the streaming potential that the electrochemical cells harvest. The solar energy is the streaming potential harvest's ultimate source. The geological formation is the energy conversion infrastructure. The civilization's electrochemical cells are the generation equipment. The DC bus is the energy distribution system. The chain from solar radiation to electrical socket passes through the geological formation's entire physical structure. The rainfall, the infiltration, the aquifer recharge, the passage network's flow, the mineral water interface's charge separation, the electrochemical cell's current generation, rather than through the combustion, the steam turbine, and the generator that the surface world's fossil fuel power plants interpose between the fossil fuel's stored solar energy and the electrical socket. The chain's length is the streaming potential harvest's most economically significant property. The geological formation's energy conversion infrastructure was built over 66 million years without the civilization's capital expenditure. The civilization's capital expenditure is the electrochemical cells installation, the generation equipment that connects to the formation's already operational energy conversion infrastructure. The generation equipment is the civilization's investment. The energy conversion infrastructure is the formation's investment. The formation's investment is the geological time that the civilization did not need to finance. The electrochemical cell array. The electrochemical cell array is the streaming potential harvest's generation infrastructure, the physical installation of the charge separation capture electrodes at the crystal tube network's passage walls where the underground river's flow produces the streaming potential at sufficient density to justify the electrode array's installation and maintenance cost. The array's installation density reflects the streaming potential harvest's spatial heterogeneity. The streaming potential's magnitude at any specific passage location is proportional to the flow velocity at that location and the mineral surface chemistry's electrokinetic coefficient at that location's specific mineral composition. The flow velocity varies across the passage network's geometric complexity, higher in the constricted passage sections whose reduced cross-section accelerates the flow, lower in the expanded chamber sections whose increased cross-section decelerates it. The electrokinetic coefficient varies with the mineral composition, higher at the calcite-rich limestone surfaces whose double-layer thickness the calcium ion's specific adsorption controls, lower at the dolomite-rich sections whose magnesium ion's different adsorption chemistry reduces the double layer's electrokinetic efficiency. The coordinating system's geological monitoring layer's passage network characterization, the acoustic survey data that maps the passage geometry and the mineral surface chemistry's spectroscopic signature, provides the spatial distribution of the streaming potential's expected magnitude across the full passage network extent. The electrode array's installation density is the energy harvest optimization's output. The coordinating system's generation planning layer identifies the passage locations where the streaming potential's expected magnitude per unit of passage wall area exceeds the electrode installation's amortized cost per unit of collected current, and specifies the electrode array's installation density at each location to maximize the ratio of collected current to installation cost. The electrode array's physical installation is the crystal tube standard's most routine maintenance operation. The electrode panels, the thin film electrode arrays whose chemical composition and surface microstructure the electrochemical cell specification determines for the specific mineral chemistry at each installation location, are mounted on the crystal tube network's external surface at the passage wall positions that the generation planning layer's installation density specification. Identifies connected to the DC bus through the Crystal Tube Standards Utility Conduits electrical wiring infrastructure and maintained by the Biological Management Protocol's coordination with the maintenance scheduled replacement cycle. The electrode panel's maintenance cycle is shorter than the Crystal Tube Standard's other infrastructure components' replacement cycles because the electrode surface's electrokinetic efficiency declines with the biofilm accumulation that the biological succession colonizes on the electrode surface. The biofilm's organic material reduces the mineral-water interface's electrokinetic coefficient by interposing the organic layer between the mineral surface's charge-determining chemistry and the water column's ionic composition. The ancestrous vitreous colony's cleaning of the electrode panel surface is the maintenance cycle's biological component. The coordinating system's acoustic management protocol includes the electrode panel surfaces in the cleaning deployments coverage map, maintaining the electrode surface's mineral water contact at the biofilm-free condition that the electrokinetic efficiency specification requires. The electrode panel's replacement cycle is the maintenance cycle's chemical component. The electrode surface's thin film composition degrades chemically over the exposure period as the dissolved minerals in the water column and the biofilm's metabolic byproducts progressively alter the thin film's surface chemistry away from the initial specification. The replacement cycle's timing is the coordinating system's electrode panel performance monitoring's output. The current density measurement at each electrode panel is compared against the installation specification's expected current density at the current flow velocity and the current mineral surface chemistry to identify panels whose current density has declined below the threshold that the replacement's cost justification requires. The cartridge-swappable replacement principle applies to the electrode panel's maintenance. The panel is a standardized format component whose dimensions and electrical connections match the Crystal Tube Standard's electrode mounting bracket, allowing the maintenance sub-standardized toolkit to remove the degraded panel and install the replacement without the specialized tools or extended maintenance access that the non-standardized component replacement would require. The replacement is the scheduled maintenance visits standard task alongside the crystal specifications cleaning confirmation and the anchor integrity monitoring's acoustic characterization. The reverse electrodialysis. The reverse electrodialysis is the electrochemical harvest's most thermodynamically elegant generation mechanism, the energy harvesting from the salinity gradient that the halocline boundary maintains between the freshwater zone above and the saltwater zone below. The gradient, that represents the free energy of mixing between the two water masses that the halocline's density gradient keeps unmixed. The free energy of mixing between freshwater and saltwater is significant. The osmotic pressure difference between a freshwater solution and a seawater solution at the cenote's salinity concentration represents approximately 0.6 megajoules per cubic meter of freshwater that could theoretically mix with the saltwater at the halocline boundary. This theoretical maximum is the salinity gradient energy's thermodynamic potential, the energy that the mixing process would release as heat if the halocline boundary were disrupted and the two water masses allowed to mix by the diffusion and advection that the boundary currently prevents. The reverse electrodialysis harvests a fraction of this thermodynamic potential without disrupting the halocline boundary. The ion exchange membranes that the reverse electrodialysis cell interposes between the freshwater zone's upper boundary and the saltwater zone's lower boundary allow the selective transport of specific ion species across the membrane without allowing the bulk fluid mixing that would destroy the halocline boundary's density gradient. The ion selective transport through the membrane generates an electrical potential difference across the membrane, the Donan potential, that the reverse electrodialysis cell's electrode pair converts to electrical current. The reverse electrodialysis installation is the electrochemical harvest's most geometrically constrained component. The halocline boundary's depth varies seasonally as the water table responds to the wet and dry seasons' recharge variation. And the reverse electrodialysis cell's membrane assembly must follow the halocline boundary's migration to maintain the necessary contact with both the freshwater zone and the saltwater zone simultaneously. The halocline tracking mechanism is the membrane assembly's depth adjustment actuator, the motorized bracket system whose position the coordinating system's halocline sensor network's current depth reading controls to maintain the membrane assembly at the halocline boundary's current position within the tolerance that the membrane's concentration gradient efficiency specification requires. The halocline tracking is the reverse electrodialysis cell's most energy-demanding operational component. The actuator's positioning energy is a parasitic load on the reverse electrodialysis cell's generation output. The tracking energy's fraction of the gross generation output is the cell's net efficiency's primary determinant. A cell whose gross generation is large relative to the tracking energy's parasitic load produces a favorable net efficiency. A cell whose gross generation is modest relative to the tracking energy produces an unfavorable net efficiency that the generation planning layer's installation cost justification may not support. The cenote's halocline is a relatively stable boundary. The seasonal depth variation is the primary source of tracking energy demand, and the seasonal variation's rate of change is the tracking actuator's required positioning velocity. The wet season's water table rise elevates the halocline by the freshwater zone's expansion that the recharge produces. The dry season's water table decline lowers the halocline by the freshwater zone's contraction. The seasonal variation's magnitude and rate are the coordinating system's halocline sensor network's most precisely characterized parameters, the parameters whose measurement accuracy the geological model's seasonal formation management most depends on. The tracking actuator's positioning velocity required to follow the seasonal variation is modest. The seasonal variation's rate of change, the centimeters per day that the water table rise or decline produces in the halocline's depth position, is slow enough that the tracking actuator's positioning requirement is within the low-power motorized bracket's actuator specification without the high-power drive that rapid depth changes would require. The parasitic tracking energy's fraction of the gross generation is therefore small, within the efficiency range that the generation planning layer's installation cost justification supports at the halocline boundary's installation location. The piezoelectric harvest. The piezoelectric sensor network was introduced in Part 2's Chapter 4 as the crystal tube standard structural health monitoring infrastructure. The piezoelectric transducers embedded in the crystal tube's borosilicate carbon composite wall material that detect the acoustic signals from geological events, maintenance activities, and biological community behavior as the primary monitoring data source for the coordinating system's formation intelligence function. The piezoelectric transducer's monitoring function generates electrical current as a byproduct. The piezoelectric effect is the conversion of mechanical deformation to electrical charge. The same physical phenomenon that the structural health monitoring uses for acoustic signal detection is the phenomenon that generates the electrical charge that the harvest circuit can collect and deliver to the DC bus as the piezoelectric harvest's generation contribution. The piezoelectric harvest generation rate is intermittent and low magnitude relative to the streaming potential and the reverse electrodialysis. The geological acoustic events whose mechanical deformation the piezoelectric transducers detect are episodic rather than continuous, and the acoustic event's energy is small relative to the continuous flow velocity's streaming potential or the halocline's salinity gradient's osmotic pressure. The piezoelectric harvest's contribution to the DC bus is the energy equivalent of the acoustic event's mechanical energy intercepted at the crystal tube wall's transducer coverage, a small, variable, episodic contribution rather than the continuous baseline that the streaming potential and the reverse electrodialysis provide. The piezoelectric harvest's most significant generation events are the collar failure acoustic signatures, the frangible ceramic collar's clean fracture that Chapter 1 of Part 7 established as the breakaway architecture's kinetic decoupling mechanism produces the highest amplitude acoustic event in the crystal tube network's monitoring record. The collar failure's acoustic energy is significantly larger than the ambient geological acoustic event's energy, and the collar failure's propagation along the crystal tube network's structural material activates the transducer network's full coverage simultaneously. The distributed energy release of the collar's fracture propagating through the network's walls produces a distributed generation event whose aggregate piezoelectric harvest across the full transducer coverage is measurable as a contribution to the DC bus's instantaneous current. The collar failure's piezoelectric generation contribution is the safety architecture's most unexpected energy contribution, the safety mechanism that the breakaway architecture specified for kinetic energy decoupling simultaneously produces the electrical energy pulse that the DC bus records as the collar failure's electrical signature. The coordinating system's geological monitoring layer uses the electrical pulse's spatial distribution across the transducer network. the differential arrival times, and the amplitude attenuation pattern as the collar failure's location identification signal alongside the acoustic propagation analysis. The energy pulse is the monitoring signal and the generation event simultaneously. The ambient geological acoustic events, the microseismic activity, the dissolution cracking, the hydraulic wave propagation contribute the continuous low-level piezoelectric generation that the monitoring network accumulates across the full design life as the geological background's mechanical energy converted to electrical current at the transducer's conversion efficiency. The cumulative contribution across the geological acoustic background's full event record is the piezoelectric harvest's design life scale generation, not significant in any single monitoring interval's energy accounting, but non-negligible in the 1,000-year design life's total energy production calculation that the founding charter's expansion reserve economics requires. Generation portfolio management. The streaming potential harvest, the reverse electrodialysis, the piezoelectric harvest, the membrane reactor's fuel cell, and the methane digester's combustion, the 5 electrical and thermal generation sources whose outputs the DC bus and the thermal management system together distribute across the installation's energy load, are the Chemostat's generation portfolio. The diversified energy production, whose combined output the energy accounting's allocation decisions distribute across the installation's energy requirements. The portfolio management's primary objective is the supply reliability, the installation's critical energy loads, the atmospheric management's active components, the coordinating system's compute infrastructure, and the light relay's biological management protocol minimum cannot tolerate interruption at any time scale shorter than the blackout protocol's passive backup system's duration. The supply reliability requires that the portfolio's combined output never falls below the critical load's aggregate requirement for any duration longer than the supercapacitor bank's bridging capacity can compensate for. The portfolio's supply reliability is the generation source's complementary intermittency profiles. Each generation source's output varies over time according to the physical process driving the generation, and the source's variation patterns are partially independent. The streaming potential harvest's flow velocity variation reflects the seasonal hydrology. The reverse electrodialysis's salinity gradient variation reflects the halocline's depth position. The piezoelectric harvest's acoustic event frequency reflects the geological activity. The membrane reactor's biological hydrogen production rate reflects the anoxic biological community's metabolic activity, and the methane digester's biogas production rate reflects the blackwater recovery's organic loading. The independence of the variation patterns means that the source's output lows are not generally correlated. The condition that produces the streaming potential harvest's minimum output, the dry season's low flow velocity, does not generally produce the methane digester's minimum biogas production simultaneously, because the dry season's reduced rainfall reduces the blackwater's organic loading rate less than the flow velocity and the anoxic biological community's metabolic rate seasonal. Variation is partially buffered by the thermal stability that the deep gallery's geological depth provides. The portfolio's combined output is therefore more stable than any individual source's output. The complementary intermittency profiles produce the supply reliability through diversity rather than through any individual source's guaranteed continuous output. The portfolio management's secondary objective is the efficiency optimization. The generation sources whose marginal generation cost is lowest, whose next unit of generation requires the least additional operational cost, should serve the load before the sources whose marginal cost is higher. The marginal cost ranking is the streaming potential harvest's lowest. The continuous underground river flow generates the streaming potential at zero marginal operating cost for the additional current that the flow produces, followed by the reverse electrodialysis's salinity gradient, whose marginal cost is the halocline tracking actuator's positioning energy at the increased current's expanded production. The membrane reactor's hydrogen production rate's marginal cost includes the biological management protocol's operational overhead. The methane digester's marginal cost includes the blackwater recovery processing. The piezoelectric harvest's marginal cost is effectively zero. The geological acoustic events generate the piezoelectric charge regardless of whether the harvest circuit collects it. The merit order dispatch, the energy economics term for the generation sequence that serves the load from the lowest marginal cost source first to the highest marginal cost source last, is the coordinating system's generation management layer's real-time operation. The continuous adjustment of each generation source's operating point to serve the current load from the merit order sequence while maintaining the supply reliability's minimum output floor above the critical load's aggregate. Requirement: energy sovereignty. The electrochemical harvest's most important governance contribution is the energy sovereignty it produces, the installation's independence from external energy supply chains as the primary energy source for the critical load's operational requirements. The surface world's energy sovereignty has been the primary strategic concern of industrial civilization since the transition from the locally available wood fuel to the fossil fuels whose geographic concentration in specific geological formations gave the formations controlling nations significant geopolitical leverage over the energy-importing civilizations whose industrial economies depended on the fuel access. The energy sovereignty's strategic significance is the inverse of the energy dependency's strategic vulnerability. The civilization that produces its own energy from domestically available resources is the civilization that the energy supply's geopolitical disruption cannot leverage against. The cenote installation's energy sovereignty is not a strategic posture. It is the consequence of the aquaforming doctrine's physical expression in the energy system's design. The installation that generates its energy from the formation's own physical processes is the installation that the surface world's energy supply chain's disruption cannot affect, not because the principality has prioritized energy independence as a strategic objective, but because the formation provides the energy through the geological, biological, and hydrological processes whose operation the physical science specifies regardless of the surface world's energy market's condition. The energy sovereignty's most specific governance significance is the principality deal's negotiating leverage. An installation that is energy independent is an installation that the host state's energy regulatory framework cannot leverage as a compliance mechanism. The energy regulatory framework's licensing, pricing, and quality standards apply to energy imports, the electricity and fuel that the installation receives from the host state's energy infrastructure. An installation that generates its own energy from internal sources has no energy imports to regulate. The host state's energy regulatory framework's leverage over the installation's governance compliance is eliminated by the energy sovereignty. The energy sovereignty is not the principality's deliberate regulatory evasion. The energy sovereignty is the formation's natural consequence of the aquaforming doctrine's design philosophy. But the governance consequence is real. The principality's energy independence is the governance independence's most concrete physical expression, and the distributed sanctuary's acoustic isolation is the most abstract physical expression, and together they constitute the principality's physical sovereignty. The sovereignty that the formation's physics provides independently of the legal category's recognition that the habitation record's accumulation is building toward. The physical sovereignty precedes the legal sovereignty. The formation's physics enforces the physical sovereignty. The legal category's recognition will formalize what the formation's physics has already established. The electrochemical harvest is the physical sovereignty's energy expression. The acoustic isolation is the physical sovereignty's communication expression. Together, they are the formation's gift to the civilization that asked what it could sustain before building anything inside it. The formation's answer is enough energy to be independent. Enough acoustic isolation to deliberate freely. Enough geological intelligence to build for 1,000 years. The civilization's question was the right question. The formation's answer was yes. The harvest's biological cost. The electrochemical harvest is not without biological cost. The reverse electrodialysis cells ion transport through the halocline boundary, and the streaming potential harvest's electrode array's presence in the passage wall's biological community's colonization substrate produce ecological impacts that the biological management protocol's ecological assessment must account for, and that the coordinating system's ecological impact budget must accommodate within the conservation standards. Acceptable range. The reverse electrodialysis cell's ion transport through the halocline boundary produces the most significant biological impact. The ion exchange membrane's selective transport of specific ion species across the halocline boundary, the sodium, chloride, and other dissolved ions whose electrochemical potential the Donnan potential harvests. Creates local concentration gradients at the membrane's freshwater and saltwater interfaces that differ from the natural halocline boundaries diffusion. Controlled gradient. The local concentration gradient's deviation from the natural gradient affects the biological community at the halocline boundary, the chemocline species whose metabolic activity depends on the specific chemical conditions that the halocline's natural gradient produces. The biological management protocol's halocline boundary assessment includes the reverse electrodialysis cell's ecological impact as a monitored parameter. The chemocline biological community's species composition and metabolic activity rate at the reverse electrodialysis cell's installation position is compared against the control positions at comparable halocline boundary sections without reverse electrodialysis installation. The comparison identifies the ecological impact's spatial extent and magnitude, which the ecological impact budget's reverse electrodialysis allocation accounts for in the total ecological impacts conservation standard assessment. The streaming potential harvests electrode array's biological impact is the biofilm succession acceleration. The electrode surface's mineral chemistry and the electrical current's electrochemical effect on the immediately adjacent water chemistry produce a microhabitat that the biological succession's pioneer community colonizes at a different rate and with a different species composition than the adjacent natural passage wall surface. The pioneer community's ecological difference, the species composition that the electrode surface's specific microhabitat conditions select for, is the streaming potential harvest's most specific ecological consequence at the biological community level. The ecological difference is not inherently negative. The pioneer community at the electrode surface may support species whose presence elsewhere in the biological community's spatial distribution would be ecologically beneficial. The biological management protocol's species composition monitoring at the electrode surface positions identifies whether the electrode-specific pioneer community's species composition differs from the natural surface's pioneer community in ways that the ecological management's target succession trajectory accommodates or that the target trajectory requires intervention to address. The biological costs acknowledgement and the ecological management's accommodation of the cost within the conservation standard is the electrochemical harvest's ecological accountability. The generation system that acknowledges its biological cost and accounts for it in the ecological impact budget is the generation system that the aquaforming doctrine's design philosophy specifies as compatible with the formation's conditions, not the generation system that produces no ecological impact, which no physical installation in a living ecological community can achieve, but the generation system whose ecological impact the monitoring quantifies and the conservation standard bounds. The harvest that acknowledges its cost is the harvest that the formation can sustain. The formation's sustainability is the harvest's operating license. The operating license is the conservation standard. The conservation standard is the ecological management's specification. The harvest operates within the license. The license is the formation's grant. The formation grants what the management earns. Cross-references. Part 2, CH2, Engineering Invisible Architecture. Part 2, CH4, The Crystal Tube Standard. Part 3, CH1, Rivers Beneath the Jungle. Part 7, CH1, Breakaway Architecture. Part 8, Section B, CH8, From Waste to Wealth. Part 10, CH1, the Chemostat. Part 10, CH3, the Compute Mesh. Part 10, CH4, the Thermal Architecture. Part 12, CH4, Regenerative Industry. For streaming potential harvest electrode array installation specification and biofilm maintenance cycle protocol, see Appendix B, Power Architecture and DC Bus. For reverse electrodialysis cell halocline tracking mechanism specification and Donnan potential generation efficiency calculation, see Appendix B, Power Architecture and DC Bus. For piezoelectric harvest circuit specification and collar failure electrical signature monitoring integration, see Appendix B, Power Architecture and DC Bus, and Appendix G, Formation Intelligence Record. For DC bus generation portfolio merit order dispatch protocol and supply reliability minimum output specification, see Appendix B, Power Architecture and DC Bus. For electrochemical harvest ecological impact budget allocation and conservation standard assessment protocol, see Appendix F, Biological Operations Manual. Pipe Dream. Part 10, The Deep Intelligence. Chapter 3. The Compute Mesh. Intelligence is the wrong word for what the coordinating system does. Intelligence implies the conscious subject, the entity that is aware of what it knows, that chooses to apply the knowledge, that experiences the application's outcome as confirmation or revision of the understanding that the choice expressed. The coordinating system has none of this. No awareness, no choice, no experience. It has the processing capability that the data input's volume and the decision output's temporal requirements demand, organized in the hardware architecture that the processing demand's specific computational characteristics specify, deployed across the physical environment that the formation's depth stratification and the installation's geographic distribution produce. The word intelligence is what the civilization uses because the civilization is inside the system and experiences the system's outputs as the intelligence that the civilization requires to manage the formation it inhabits. The anchor integrity model that tells the terraform operator whether the anchor zone is safe for the next gallery ring installation. The biological community's succession trajectory model that tells the biological management protocol whether to advance or delay the next cleaning cycle. The geological stress field model that tells the safety architecture's collar specification whether to revise the threshold at the failure location. These outputs feel like intelligence to the user of the outputs, because the outputs are the information that the civilization needs to make the decisions that the formation's thousand-year management requires. The coordinating system does not feel like intelligence from inside the system. It is computation. The transformation of data inputs into decision outputs through the mathematical operations that the processing architecture executes at the rates and the precisions that the input volumes and the output timescales demand. The compute mesh is the physical infrastructure in which this computation occurs, the distributed array of classical and quantum processing nodes whose physical locations, interconnection topology, and computational function assignments together constitute the platform on which the coordinating system's full processing capability operates. The mesh is not in a data center. It is in the formation, distributed across the depth from the surface tier's communication infrastructure to the deep gallery's quantum interference nodes, networked through the crystal tube's fiber optic and acoustic communication channels, powered from the DC bus's electrochemical harvest, and cooled by the thermal management architecture that the deep gallery's geological stability provides. The formation is the data center. The data center is the formation. The computation is the formation's self-knowledge, processed by the civilization's infrastructure. The classical neural compute layer. The classical neural compute layer handles the coordination tasks whose computational demands are high in data volume and low in interpretive depth: the production planning, the maintenance scheduling, the visitor management, the biological monitoring species identification, the atmospheric management's control loop, and the safety architecture's real-time response. These are the tasks that the classical compute architecture, the silicon transistor arrays whose gate densities the semiconductor industry has been scaling for 7 decades, handles better than any alternative architecture. High throughput, low latency, massive parallelism, predictable execution time. The classical neural compute layer's physical distribution reflects the latency requirements of the tasks it handles. The production planning's decision cycle is hours to days, tolerating the communication latency that the deep gallery's nodes introduce into the calculation before the result reaches the surface tier's management interface. The atmospheric management's control loop cycle is seconds to minutes, requiring the processing node's proximity to the atmospheric management sensors and actuators that the control loop's feedback requires at low latency. The safety architecture's real-time response to collar failure events is milliseconds, requiring the processing that the local crystal tube section's embedded node provides without communication latency to the central mesh. The distribution is a latency hierarchy. The deepest processing nodes in the deep gallery's compute infrastructure handle the longest cycle tasks whose communication latency to the surface tier's management interface is acceptable at the geological intelligence function's temporal horizon. The shallowest processing nodes in the surface tier's communication infrastructure handle the shortest cycle tasks whose communication latency must be below the control loop's stability requirement and the real-time response's timing window. The classical neural compute layer's most computationally demanding task is the digital twin's real-time update, the continuous integration of the sensor network's full data stream into the formation model's current state representation. the three-dimensional formation model that Chapter 6 of Part 2 established as the coordinating system's primary formation intelligence instrument. The digital twins update rate is the formation model's temporal resolution, the frequency at which the formation model's state representation reflects the current sensor network's data rather than the most recent update's calculation. The digital twins update rate is the compute layer's throughput requirement's most demanding driver. The sensor network's full data stream, the piezoelectric monitoring's continuous acoustic data, the biological monitoring's imaging data, the halocline sensor's water chemistry data, the structural health monitoring's anchor integrity data, and the atmospheric management's pressure and composition data, arrives at the classical compute layer at a combined data rate that the processor arrays. Input bandwidth and the formation model's update algorithm's computational complexity together determine as the feasible update rate. The feasible update rate is not the continuous update that the sensor stream's data rate would theoretically support. The formation model's update algorithm's computational complexity exceeds the processor array's throughput at the full sensor data rate, requiring the update scheduling that the coordinating system's data management layer implements as the formation model's sampling strategy. The selection of the sensor data's temporal and spatial subsets that the formation model's update algorithm processes at the processor array's available throughput, producing the update rate that the throughput allows rather than the update rate that the continuous data stream would require. The sampling strategy's specification is the classical compute layer's most consequential architectural decision. The sampling subset that the update rate's computational constraint requires must include the formation data that the formation model's current state representation is most sensitive to. The sensor readings whose most recent values have the largest effect on the formation model's output at the next governance decisions evaluation. The sampling strategy is the formation model's information prioritization, the decision about which formation data is most important to know now, given the formation model's current state and the governance decisions that the current management interval requires. The quantum interference nodes. The quantum interference nodes handle the pattern recognition tasks whose computational demands are low in data volume and high in interpretive depth. The geological stress field's long-horizon trajectory projection, the ecological succession's multi-century evolutionary trajectory, the legal strategy's geopolitical context pattern, and the governance record's generational institutional pattern. These are the tasks that the classical compute architecture handles poorly, the problems whose solution space is too large for the brute force search that the classical processor executes, whose solution quality degrades faster than the classical processor's throughput grows as the problem's temporal horizon extends. The quantum interference node's computational advantage for these tasks is the quantum superposition's ability to represent and process the exponentially large solution space simultaneously rather than sequentially. The classical processor that evaluates the geological stress field's million possible future states one at a time requires a million evaluations to find the highest probability trajectory. The quantum processor that represents all million states simultaneously in the superposition and applies the trajectory projections operations to the superposition in a single step finds the highest probability trajectory at a cost that grows polynomially with the problem's complexity rather than exponentially. The polynomial versus exponential scaling is the quantum compute advantage's technical characterization, and the temporal horizon of the pattern recognition tasks is where the scaling difference becomes the qualitative capability difference rather than merely the quantitative speed difference. A classical processor that requires 1 trillion operations to project the geological stress field's 1,000-year trajectory and executes 1 billion operations per second would require 1,000 seconds. For the calculation, a significant computational cost that the coordinating system's governance decision timeline can potentially accommodate. The same processor applied to the 10,000-year trajectory would require 1 quadrillion operations, 1 million seconds. The geological timescale's inadequate resolution for the governance decision's planning horizon. The quantum processor's polynomial scaling allows the 10,000-year trajectory's calculation within the governance decision's planning horizon because the polynomial gross absolute computational cost remains within the quantum processor's available throughput even at the extended temporal horizon. The geological model's deep time pattern recognition is accessible to the quantum compute architecture and inaccessible to the classical compute architecture at the temporal resolution that the formation's management across the 1,000-year design life requires. The quantum interference node's physical placement in the deep gallery's environmental isolation is the compute mesh's most geologically specific design decision. The photonic qubit technology's operating specification requires the temperature stability, the magnetic isolation, and the acoustic isolation that the deep gallery's geological depth provides as the passive environmental condition, rather than as the active environmental control that the surface world's quantum compute facilities must maintain through cryogenic infrastructure. The deep gallery's temperature stability at the geological depth's thermal mass is the photonic qubit's operating environment within the specification's tolerances, not the absolute temperature stability that the superconducting qubit requires, but the parts per million level stability that the photonic qubit's wavelength-sensitive resonant cavities require for the coherence time that the pattern recognition algorithm's circuit depth demands. The photonic qubit's wavelength sensitivity is the quantum interference node's most precisely specified environmental requirement. The optical frequency of the photonic qubit's resonant mode must be stable to the fractional hertz level across the quantum circuit's execution time for the quantum interference to remain coherent through the algorithm's full computational depth. The temperature variation that the deep gallery's geological depth produces is within the fractional hertz stability's thermal budget for the photonic qubit technology's temperature coefficient, the temperature-to-frequency relationship that the resonant cavity's thermal expansion specifies at the qubit's operating wavelength. The mesh topology. The classical compute nodes and the quantum interference nodes are connected in the compute mesh's network topology, the communication infrastructure whose bandwidth, latency, and physical medium the data transfer requirements between the distributed nodes determine. The mesh topology is not the star topology that the surface world's cloud computing architecture typically deploys, the single central data center to which all the edge nodes connect and from which all the coordination services flow. The star topology's single center is the mesh's single vulnerability. The central data center's failure is the entire system's failure, and the star topology's concentration of function in the center is the concentration of vulnerability in the same location. The mesh topology's distributed architecture is the compute infrastructure's reliability expression of the safety architecture's DSI principle. The compute function that is distributed across the mesh's nodes cannot be eliminated by the single node's failure any more than the crystal tube network's atmospheric integrity can be eliminated by the single section's collar failure. The mesh is designed to continue operating with degraded capability when any subset of nodes fails, with the task allocation that the coordinating system's mesh management layer redistributes to the surviving nodes at the capability level that the surviving node's aggregate capacity supports. The mesh management layer's task redistribution is the compute infrastructure's graceful degradation, the full capability state, all nodes operational at rated capacity, supports the full coordinating system function at the update rates and the latency targets that the formation management's full specification requires. The degraded state, a subset of nodes operational following a geological event's physical damage or a power failure's operational interruption, supports the critical function subset at reduced update rates and increased latency that the blackout protocol's operational specification identifies as the minimum capability for the survival operations that the critical management period's duration requires. The degraded state's critical function subset is the governance decision's minimum informational requirement during the formation event's management period, the atmospheric management's control loop, the safety architecture's real-time response, and the terraform operator's formation condition assessment. All three functions' informational requirements can be served by the classical compute node's most proximate subset, the local crystal tube section's embedded nodes, without communication to the deep gallery's quantum interference nodes or the distant mesh nodes. The degraded state is the local computation's survival mode, the formation's immediate neighborhood's classical nodes providing the immediate formation conditions critical monitoring without the pattern recognition's long-horizon intelligence that the quantum interference nodes provide and that the critical management period's immediate decisions do not require. The mesh topology's communication medium reflects the physical environment's diversity across the installation's depth extent. The surface tier's communication infrastructure uses the surface world's fiber optic channels whose bandwidth the surface tier's data rate requirements demand. The freshwater zone's crystal tube network uses the acoustic communication channels whose bandwidth the geological medium's acoustic propagation supports, and the deep gallery's internal communication uses the Optical fiber, whose isolation from the ambient electromagnetic environment the deep gallery's shielded installation provides. The three communication media's bandwidth hierarchy reflects the computation's depth stratification. The surface tier's fiber optics highest bandwidth supports the surface tier's highest data volume tasks. The crystal tube's acoustic communications intermediate bandwidth supports the freshwater zone's intermediate data volume tasks. And the deep gallery's internal optical fiber's highest isolation bandwidth supports the quantum interference node's lowest volume, highest fidelity internode communication that the quantum circuit's gate operations require for the quantum coherence's maintenance across the distributed quantum computation. The digital twin's architecture. The digital twin is the compute mesh's most architecturally specific application, the continuously updated three-dimensional model of the formation's full physical, biological, chemical, and governance state, whose representation the classical compute nodes maintain, and whose deep pattern analysis the quantum interference nodes perform. The digital twin is not a rendering. It is a model, the mathematical representation of the formation's current state at the spatial resolution that the sensor network's measurement density produces and the temporal resolution that the update algorithm's computational throughput allows. The rendering of the digital twin as the visual interface that the Terraform operator's monitoring review presents on the management display is the digital twin's most visible output, but not its primary function. The primary function is the governance decision's informational foundation, the formation's current state's quantitative description that the Terraform operator's concurrent authorization, the stocking algorithm's ecological constraint, and the Redeemer framework's deliberative process information disclosure requirement all draw from as the authoritative reference for the formation's current condition. The digital twin's architecture is the formation's information architecture, the data model that the formation's full physical complexity requires to be represented at the resolution that the governance decision's informational requirement demands. The data model's design reflects the formation's specific character, the three-dimensional spatial complexity of the dissolution void geometry, the biological community's species composition and spatial distribution, the water chemistry's vertical stratification, and the geological stress field's three-dimensional tensor, rather than the generic data model that the surface world's digital twin platforms apply to the manufactured environments whose geometric regularity and material uniformity simplify the data model's required complexity. The formation-specific data model is the digital twin's most significant software engineering contribution. The representation of the 66-million-year-old geological formation's complexity in the quantitative model that the sensor network's measurements populate and the governance decision's informational requirement queries is the foundational software architecture whose correctness determines whether the compute mesh's processing of the digital twin's data produces the formation intelligence that the civilization's management requires. The data model's correctness is the geological model's scientific validity. The mathematical relationships between the sensor measurements and the formation state variables that the data model specifies must reflect the physical, chemical, and biological science that governs the formation's actual behavior. A data model whose relationships are incorrect, whose representations of the connection between the halocline's depth and the water table's height, or the connection between the biological community's species composition and the cleaning cycle's timing, or the connection between the geological stress field and the collar failure's probability, produces formation intelligence whose incorrectness the governance decision's outcomes will eventually reveal as the divergence between the digital twin's predictions and the formation's actual behavior. The digital twin scientific validity is the research commons' most important ongoing contribution to the compute mesh's intelligence function. The research commons formation science, the geological, biological, chemical, and ecological research that the longitudinal datasets accumulation supports, continuously improves the data model's mathematical relationships as the formation science's understanding advances. The digital twin improves as the formation science improves. The formation science improves as the digital twin's predictions are tested against the formation's actual behavior, and the divergences are investigated as the research questions that the formation science's advancement requires. The digital twin's validation is the formation intelligence's scientific foundation. The formation that is correctly modeled is the formation that the civilization can manage with confidence in the intelligence that the model's processing produces. The confidence is not certainty, The formation model has uncertainties, the sensor network has measurement noise, the update algorithm has approximations, and the quantum interference node's pattern recognition has the probabilistic character that the quantum computation's superposition collapse produces. But the confidence is calibrated. The digital twin's uncertainty quantification at each model output is the governance decision's uncertainty awareness, the knowledge of how confident the civilization can be in the formation intelligence that the compute mesh provides. The calibrated confidence is the civilization's relationship to its own intelligence, not the false certainty that the governance decision that the digital twin's recommendation requires is the correct decision, but the quantified uncertainty that the governance decision must take account of in designing the reversible choices and the monitoring intervals that the uncertainty's magnitude specifies as prudent. The governance intelligence function. The compute mesh's most distinctive contribution to the governance architecture is the governance intelligence function, the pattern recognition capability that the quantum interference nodes provide for the formation's long-horizon behavior, the Redeemer framework's institutional pattern, and the legal strategy's geopolitical context. The intelligence inputs that the governance decision's long-horizon planning requires and that the classical compute architecture cannot provide at the temporal resolution and the pattern depth that the thousand-year design life's governance requires. The governance intelligence function is not the governance decision. The quantum interference nodes do not decide what the expansion program's next deployment target should be, what the legal strategy's next negotiating position should communicate, or what the Commons governance protocol's quota allocation should specify. The quantum interference nodes identify the patterns in the formation's geological data, the Redeemer framework's deliberative history, and the geopolitical context indicators that the governance decisions planning must incorporate to avoid the long-horizon failure modes that the short-horizon decision's optimality produces at the long-horizon's timescale. The long-horizon failure mode is the governance decision's most insidious risk. The decision that is optimal for the current management interval's objectives may be the decision that the long horizon's trajectory analysis identifies as the precursor to the formation degradation, the governance institution's erosion, or the legal strategy's premature political confrontation that the habitation record's current evidence base cannot sustain. The short-horizon optimization and the long-horizon trajectory are different optimization problems, and the short-horizon decision that ignores the long-horizon trajectory produces the Amazon lesson's institutional form, the decision that is locally optimal and globally catastrophic. The quantum interference node's long-horizon trajectory analysis is the governance intelligence function's primary value, the pattern recognition that identifies the long-horizon trajectory from the formation's current state, the governance record's institutional pattern, and the geopolitical context's indicators. The intelligence that allows the governance decision to be both short-horizon optimal and long-horizon compatible rather than trading one for the other. The governance intelligence function's most specific output is the terraform operator's concurrent authorizations formation condition assessment. The quantum interference node's geological stress field trajectory analysis is the formation condition assessment's deepest layer, identifying the stress concentration patterns in the formation structural data that the classical compute node's current state representation displays as the numerical values, but whose significance for the thousand-year design life's structural evolution requires the pattern recognition that the quantum computation provides. The terraform operator, who reviews the formation condition assessment with the geological stress field trajectory's pattern recognition output, is the terraform operator whose concurrent authorization reflects not only the current state's numerical values, but the long-horizon trajectory's pattern. The formation's geological communication at the timescale that the classical compute's numerical accuracy and the quantum compute's pattern depth together translate into the professional judgment that the governance decision requires. The professional judgment is the governance decision's human layer. The compute mesh is the governance decision's informational layer. The formation is the governance decision subject and the information source. The thousand-year design life is the governance decision's temporal horizon. The compute mesh makes the horizon visible. The terraform operator makes the visibility actionable. The governance decision makes the actionable consequential. The mesh's failure modes. The compute mesh's failure modes are the governance intelligence's vulnerability points, the conditions under which the formation intelligence that the mesh produces is incorrect, incomplete, or unavailable, conditions that the governance decision's risk management must account for as the probability of false confidence in the formations condition. The sensor network's failure is the most common failure mode. The individual sensor that has drifted out of calibration, the biological monitoring camera whose lens the fouling community has obscured before the maintenance cycle's next cleaning visit, the halocline sensor whose electrode has been corroded by the saltwater column's chemical activity between maintenance replacements. The individual sensor failure reduces the digital twin's spatial coverage at the failed sensor's location. The formation model's state representation at the failure location must be interpolated from the adjacent sensor's measurements rather than directly measured by the failed sensor. The interpolation's uncertainty is higher than the direct measurement's uncertainty, and the digital twin's uncertainty quantification at the failure location reflects the interpolation's increased uncertainty in the formation condition assessment's output. The terraform operator who reviews the formation condition assessment at a location where the sensor network has failed sees the increased uncertainty indicator alongside the interpolated state values. The digital twin's communication that the formation intelligence at this location is less reliable than the directly measured location's intelligence. The model update algorithm's numerical divergence is the rarest but most consequential failure mode. The iterative numerical algorithm that updates the formation model state from the sensor measurements can diverge when the sensor measurements contain sufficient noise or when the formation state has moved into a regime that the model's numerical stability analysis did not anticipate. The divergence produces the formation model's state representation that is numerically large but physically meaningless, the unbounded solution that the stability analysis's failure to anticipate the specific regime's instability produced. The coordinating system's mesh management layer monitors the formation model state for the divergence signature, the specific patterns of rapid state variable growth that distinguish the numerical divergence from the rapid physical change that the formation event produces. The divergence detection triggers the formation model's reset to the last stable state before the divergence began, which the digital twin state history archive maintains as the rollback reference at the update cycle's temporal resolution. The quantum decoherence is the quantum interference node's specific failure mode, the loss of the quantum superposition's coherence that the ambient temperature variation, the acoustic vibration, or the electromagnetic interference introduces when the environmental isolation's quality has degraded below the coherence times maintenance requirement. The decoherence produces the quantum circuit's premature collapse to the classical state, the pattern recognition result that reflects the collapsed state rather than the full superposition's interference, producing the classical compute's local optimum rather than the quantum computation's global optimum. The decoherence detection is the quantum interference node's internal error correction. The quantum circuit's ancilla qubits monitor the primary qubit's coherent state and trigger the error correction protocol when the decoherence signature is detected. The error correction protocol's response is the computation's restart from the last coherent checkpoint rather than the continuation of the decoherent computation, the quantum compute equivalent of the classical processor's exception handler that restarts the computation from the last valid state when the numerical error detection identifies the invalid state. What the compute mesh produces. The compute mesh produces formation intelligence. The formation intelligence is the governance decision's informational foundation. The governance decision is the civilization's management of the formation's conditions. The conditions are what the formation allows. What the formation allows is what the civilization can sustainably inhabit. The mesh is the translation layer between the formation's physical reality and the civilization's institutional capacity to respond to that reality. The formation communicates through its geological, biological, and hydrological processes. The sensor network measures the communications. The classical compute layer processes the measurements into the formation model's current state. The quantum compute layer projects the current state's long horizon trajectory. The digital twin integrates the current state and the trajectory into the formation intelligence. And the terraform operator's professional judgment translates the formation intelligence into the concurrent authorization that the Redeemer framework's governance decision requires. The translation's quality determines the civilization's management quality. The formation intelligence that accurately represents the formation's current condition and correctly projects the formation's long horizon trajectory produces the governance decisions that maintain the formation's conditions within the ecological management's conservation standard across the 1,000-year design life. The formation intelligence that is inaccurate, sensor failures undetected, model divergences uncorrected, quantum decoherence unrecognized, produces the governance decisions that the Amazon lessons governance failure produced, the decisions that are locally optimal and globally catastrophic. The compute mesh is the civilization's primary insurance against the Amazon lessons recurrence, the intelligence infrastructure that makes the governance decisions' informational foundation as accurate, as complete, and as long-horizon aware as the physical science and the engineering capability together allow. The insurance is not perfect. The mesh has failure modes, the formation model has uncertainties, the quantum computation has probabilities. But the insurance is the best available implementation of the founding charter's design philosophy, the governance decision that is as well informed as the physical science and the engineering capability can make it is the governance decision that the aquaforming doctrine sans a priori approach requires. The formation is more knowledgeable about itself than the compute mesh can model. The compute mesh is more knowledgeable about the formation than the unaided human cognition can access at the formation's spatial and temporal scales. The terraform operator's professional judgment is more contextually sensitive than the compute mesh's algorithmic output can be. The Redeemer framework's deliberative process is more politically legitimate than the terraform operator's individual authority. Each layer adds what the preceding layer cannot provide. Together, they constitute the governance intelligence's full architecture. The formation's 66 million years, the sensor network's continuous measurement, the classical compute's real-time processing, the quantum compute's long-horizon pattern recognition, the terraform operator's professional judgment, and the Redeemer framework's deliberative legitimacy. The full intelligence stack that the civilization's management of the geological formation's thousand-year inhabitation requires. The compute mesh is the intelligence stack's technological layer. It is not the most important layer. It is the layer that makes the other layer's intelligence visible to the governance decision's informational requirement. The formation's intelligence was always there. The compute mesh makes it visible. The governance decision makes it consequential. Cross-references. Part 2, CH2, Engineering Invisible Architecture. Part 2, CH4, The Crystal Tube Standard. Part 7, CH1, Breakaway Architecture. Part 7, CH4, Living Through Failure. Part 9, CH4, Redeemer as Governance OS. Part 10, CH1, The Chemostat. Part 10, CH2, Electrochemical Harvest. Part 10, CH4, The Thermal Architecture. Part 10, CH6, ESI as Co-Creating Partner. For classical compute node distribution specification and task allocation latency hierarchy, see Appendix G, Formation Intelligence Record. For quantum interference node photonic qubit operating specification and deep gallery environmental isolation requirement, see Appendix G, Formation Intelligence Record. For digital twin data model architecture specification and formation state variable mathematical relationship definitions, see Appendix G, Formation Intelligence Record. For mesh topology communication medium specification and degraded state critical function subset protocol, see Appendix G, Formation Intelligence Record. For sensor failure detection and digital twin uncertainty quantification protocol, see Appendix G, Formation Intelligence Record. For quantum decoherence detection and error correction restart protocol, see Appendix G, Formation Intelligence Record. Pipe Dream. Part 10, The Deep Intelligence. Chapter 4, The Thermal Architecture. Heat flows downward in the intuition and upward in the physics. The surface world's thermal intuition, the inheritance of millions of years of biological sensitivity to the gravitational relationship between the body's heat and the environment's cold, places warmth above and cold below. The sun is overhead, the Earth's surface is below the sun and absorbs the sun's warmth, and the underground is the place where the cold is, where the root cellar's chill preserves the summer's harvest through the winter, where the cave's constant temperature is cooler than the summer air above it. The physics is more specific. Heat flows from higher temperature to lower temperature through the mechanisms of conduction, convection, and radiation, and the direction of the flow is determined entirely by the temperature gradient rather than by the gravitational direction that the intuition associates with warmth. The sun heats the surface world from above, and the surface world's near-surface geological formations are cooler than the surface. That much the intuition captures correctly. But the deep geological formations are warmer than the near-surface formations because the Earth's internal heat flux, the thermal energy that the radioactive decay in the Earth's crust and mantle continuously produces, flows outward toward the surface against the gravitational intuition's expected direction. The geothermal gradient increases the temperature with depth, and the deep geological formation is warmer than the formation above it, and the temperature difference drives the heat flux upward toward the cooler surface rather than downward toward the hotter interior. The cenote's thermal architecture exploits both directions. The geological depth's warmth as the chemostat's geothermal thermal loop's energy source, and the formation's passive thermal stability. The geological thermal mass's insulation of the deep aquifer's water column from the surface temperature's daily and seasonal variation as the production system's temperature control. The thermal architecture is the formation's thermal physics organized for the civilization's thermal management, not the mechanical refrigeration and the fossil fuel combustion that the surface world's industrial thermal management requires, but the formation's own temperature gradient and thermal mass engaged by the installation's passive heat exchange infrastructure. The formation's thermal stratification. The cenote's water column is thermally stratified. The surface zone's temperature is highest, reflecting the surface world's ambient temperature and the solar radiation's warming of the cenote opening's water surface. The freshwater zone's mid-column temperature is intermediate, reflecting the aquifer's groundwater temperature that the subsurface geology maintains through the thermal buffering of the large water volume's thermal mass, and the deep gallery's temperature is the geological gradients expression, slightly elevated above the freshwater zone's groundwater temperature by the chemostat's metabolic heat production and the geological substrate's geothermal heat flux. The stratification is not a single stable gradient. It is a dynamic thermal structure whose specific temperature profile at each depth reflects the seasonal variation in the surface zone's heat input from the ambient air temperature and the solar radiation, the thermal buffering of the freshwater zone's large water mass, and the steady-state balance between the chemostat's metabolic heat production and the surrounding geological medium's heat conduction capacity at the deep gallery depth. The surface zone's temperature variation is the seasonal component. The cenote opening's air exchange with the surface world's atmosphere imports the diurnal and seasonal surface air temperature variation into the uppermost water column, producing the temperature oscillation that the biological management protocol's seasonal calibration accounts for in the production system's species depth assignments and the therapeutic protocol's depth recommendations. The surface zone's maximum temperature occurs at the dry season's peak when the surface air temperature is highest and the solar radiation's angle maximizes the light column's heating of the uppermost water layer. The freshwater zone's mid-column temperature stability is the thermal mass's product. The large volume of water in the freshwater zone's depth range buffers the surface zone's temperature variation through the specific heat capacity of water's large thermal inertia. The quantity of heat required to change the water volume's temperature by 1 degree Celsius exceeds the seasonal heat flux's capacity to change the large volume's temperature faster than the seasonal cycle's rate. The freshwater zone's mid-column temperature approaches the groundwater temperature that the regional aquifer's water table maintains at the formation's depth, a temperature that reflects the regional geological conditions rather than the surface world's seasonal variation. The groundwater temperature at the freshwater zone's mid-column depth is the most operationally significant temperature in the installation's thermal architecture. The production system's aquaculture production operates within this temperature range. The longevity program's therapeutic protocol specifies the therapeutic depth partially on the basis of this temperature's effect on the enrolled participant's metabolic rate, and the crystal tube standard structural specification accounts for the thermal cycling that the surface zone's temperature variation produces in the structural materials relative to the mid-column's more stable thermal environment. Passive thermal stability. The formation's passive thermal stability is the installation's most valuable thermal asset and the one whose economic value the energy accounting quantifies most directly by comparison with the active thermal management's energy costs that the surface world's equivalent production system would require. The passive thermal stability is the geological thermal mass's product. The limestone formation that surrounds the cenote's freshwater zone has been storing the regional geological thermal equilibrium, the balance between the geothermal heat flux's upward contribution and the surface world's temperature's downward influence. For geological timescales that have produced a thermal state whose resistance to perturbation by the installation's operational heat loads is determined by the thermal mass's thermal capacitance and the thermal conductivity's heat removal rate. The thermal capacitance is the product of the limestone's specific heat capacity and the mass of the formation that the installation's operational heat load can thermally influence. The thermal conductivity's heat removal rate is the product of the limestone's thermal conductivity and the temperature gradient that the installation's heat load produces between the formation's interior and the regional geological thermal equilibrium's temperature at the formation's exterior boundary. Together, the thermal capacitance and the heat removal rate determine the formation's thermal response time to the installation's operational heat load, the time constant that characterizes how rapidly the formation's temperature changes in response to a sustained heat load. The formation's thermal response time to the installation's operational heat loads is long, measured in years to decades rather than hours to days. The operational heat loads that the chemostat's metabolic activity, the compute mesh's heat dissipation, and the crystal tube network's electrical resistance losses produce are too small relative to the formation's thermal mass to produce significant temperature changes within the geological response time. The formation's temperature is effectively constant for the operational timescales that the production system's management, the therapeutic protocols, depth assignments, and the construction program's material specifications must account for. The passive thermal stability's economic value is the refrigeration energy that the installation does not spend. The production system's aquaculture species' optimal temperature range is within the formation's passive thermal stability's maintained temperature range, requiring no active cooling. The compute mesh's quantum interference node's operating temperature requirement is within the formation's passive thermal stability's maintained temperature range, requiring no active cooling. The longevity program's therapeutic depth assignment's temperature requirements are within the formation's passive thermal stability's temperature gradient, requiring no active temperature management beyond the depth assignment selection. The formation provides the temperature control. The civilization does not manufacture it. The economic value is the manufacturing's energy cost that the formation eliminates. The thermal management system's architecture. The thermal management system's architecture reflects the installation's dual thermal challenge: the deep gallery's elevated temperature from the chemostat's metabolic heat production and the geothermal heat flux, and the surface zone's variable temperature from the surface world's seasonal variation. The two thermal challenges require different management approaches whose architectures the thermal management system provides in the same physical infrastructure. The deep gallery's elevated temperature management is the heat removal challenge. The chemostat's metabolic heat production adds thermal energy to the deep gallery's water column at the rate the biological community's metabolic activity determines, and the geothermal heat flux adds thermal energy at the rate the geological heat conduction determines. The combined heat input must be removed from the deep gallery's water column at the same rate to maintain the steady-state temperature that the quantum interference node's operating specification and the chemostat's biological community's productivity optimization require. The heat removal mechanism is the geothermal thermal loop's closed circuit in reverse. The working fluid that the chemostat's geothermal energy harvest extracts heat from the geological substrate's warmer surface for the surface tier's thermal applications carries the working fluid back to the deep gallery, where the working fluid is cooler than the biological community's metabolic zone. The cooler returning working fluid absorbs heat from the biological community's metabolic zone through the heat exchanger panels positioned within the chemostat's three galleries, extracting the metabolic heat and the geothermal heat at a combined rate that the working fluid's flow rate and temperature difference together determine. The working fluid's flow rate is the thermal management system's primary control variable. The pump that circulates the working fluid through the closed circuit operates at the flow rate that the thermal management layer's control algorithm specifies to maintain the deep gallery's water column temperature within the operating specifications range. The control algorithm's input is the deep gallery temperature sensor network's current temperature readings. The output is the pump's flow rate set point. The control logic is the proportional integral feedback that minimizes the temperature deviation from the set point. The surface zone's variable temperature management is the temperature buffering challenge. The surface zone's temperature oscillation between the dry season's maximum and the wet season's minimum produces the thermal cycling that the surface zone's structural materials must accommodate and that the surface zone's biological community must sustain within the management protocol's succession target range. The thermal buffering mechanism is the surface zone's design that minimizes the operational heat loads in the surface zone's thermal environment. The design that places the thermally sensitive components and the thermally sensitive biological communities at the depths where the formation's thermal stability is highest rather than in the surface zone where the thermal cycling is most pronounced. The thermal sensitive component placement at thermally stable depths is the crystal tube standard's most specific thermal design provision. The compute mesh's classical nodes whose operation generates significant heat are placed in the mid-column zone where the formation's thermal mass provides the cooling that the active thermal management would otherwise require. The quantum interference nodes whose temperature sensitivity is highest are placed in the deep gallery where the geological depths. Thermal stability is greatest. And the surface zone's compute infrastructure is limited to the communication nodes whose heat dissipation is lowest and whose thermal sensitivity is most compatible with the surface zone's temperature oscillation. The thermal gradient as productivity gradient. The thermal stratification that the formation's passive thermal architecture produces is not only the temperature control infrastructure, it is the production system's ecological driver, the therapeutic protocol's depth assignment's primary determinant, and the geological intelligence function's most directly legible formation parameter. The production system's ecological driver, the freshwater zone's thermal gradient from the surface zone's seasonal maximum to the halocline boundary's minimum is the primary determinant of the production system's species depth assignments that Chapter 2 of Part 8 Section be established as the vertical tower's production efficiency foundation. The giant freshwater prawn's optimal growth rate temperature, the cave-adapted tilapia's preferred temperature, the freshwater lobster's cold preference metabolic profile. All of these are the thermal gradient's biological expression. The specific organisms whose evolutionary history and metabolic specialization has optimized their productivity at the specific temperature that the formation's thermal gradient provides at the specific depth where the species' optimal growth rate's temperature
requirement is met.
The thermal gradient is not the production system's constraint that must be managed around. It is the production system's organizing principle. The vertical stratification of production species by their optimal temperature is the thermal gradient's biological exploitation, the production system's organization by the formation's physical character rather than by the surface world's aquaculture facilities' temperature-controlled uniformity. The therapeutic protocol's depth assignment's primary determinant. The longevity program's therapeutic depth assignments reflect the therapeutic pressure range's primary consideration, but the therapeutic temperature's secondary consideration is the depth assignment's additional optimization input. The enrolled participant whose blood work indicates a biological response to temperature, whose inflammatory markers reduction or telomere extension rate shows the temperature-dependent enhancement that the medical monitoring's longitudinal dataset identifies, receives the depth assignment that provides both the therapeutic pressure range and the therapeutic temperature range that the participant's specific biological profile indicates as the most productive combination. The thermal gradient's therapeutic significance is the medical monitoring's most recent analytical frontier. The founding installation's longitudinal dataset's multi-decade accumulation has produced the statistical power to identify the temperature-specific components of the therapeutic protocol's biological outcomes that the shorter dataset's smaller sample sizes could not distinguish from the pressure-specific components. The therapeutic temperature's specific contribution to the telomere extension rate, the inflammatory marker reduction, and the cardiovascular efficiency improvement is the quantified benefit that the depth assignment's temperature optimization adds to the pressure optimization's established therapeutic framework. The geological intelligence's most directly legible parameter. The formation's thermal stratification is the geological intelligence function's most stable and most precisely characterized parameter. The temperature profile that the halocline sensor network's thermistors measure at each monitoring interval is the digital twin's most reliable current state variable, because the thermal mass's slow response time means that the temperature profile's current measurement accurately represents the formation's thermal state at the timescale that the governance decision's planning horizon requires. The temperature profile stability as the digital twin's most reliable parameter makes the temperature monitoring the geological intelligence's primary validation check. The formation model's other state variables, the geological stress field, the biological community's species composition, the water chemistry's dissolved mineral concentrations, are less reliably characterized at the temporal resolution that the sensor network's measurement density and the model update algorithms. Computational throughput allow. The temperature profile's high reliability provides the formation model's calibration anchor, the state variable against which the model's other state variables' predictions are validated and whose discrepancy from the model prediction signals the model calibration error that the geological intelligence update requires. Thermal energy storage. The thermal management system's passive thermal architecture produces more thermal energy at some temporal periods than the installation's thermal loads require. The dry season's lower chemostat metabolic activity reduces the geothermal thermal loop's harvest below the surface tier's thermal application demand during the period of highest surface temperature. And the wet season's higher chemostat metabolic activity produces more thermal energy than the surface tier's reduced demand requires during the period of lower surface temperature. The thermal energy storage is the thermal management system's temporal smoothing mechanism, the accumulation of thermal energy during the periods of production excess, and the withdrawal of accumulated thermal energy during the periods of production deficit, producing the continuous thermal supply that the surface tier's applications require at a rate that the thermal storage's buffering capacity maintains above the application demand's seasonal minimum. The thermal energy storage medium is the formation's own water column. The large volume of the freshwater zone's water at the mid-column depth provides the thermal capacitance that the seasonal thermal energy accumulation requires. The specific heat capacity of the water volume multiplied by the permissible temperature range within the thermal storage's operating specification determines the thermal storage capacity that the water column provides without the additional capital cost of the surface world's thermal energy storage infrastructure. The permissible temperature range within the thermal storage's operating specification is the constraint that the production systems and the therapeutic protocol's temperature requirements impose on the thermal storage's operation. The temperature range that the water column's temperature can vary within without exceeding the production system's species depth assignments temperature tolerances and the therapeutic protocol's depth assignments temperature requirements. The thermal storage capacity that the permissible temperature range and the water column volume together provide is the thermal management system's most precisely calculated design parameter, the calculation whose accuracy determines whether the thermal storage's seasonal buffering capacity is adequate for the seasonal production demand imbalance that the formation's thermal dynamics produces. The calculation's accuracy depends on the geological model's thermal characterization, the formation model's specification of the chemostat's seasonal metabolic activity variation, the surface tier's seasonal thermal application demand variation, and the freshwater zone's water column thermal dynamics, the heat transfer rates between the water column's different depth layers, between the water column and the surrounding limestone formation, and between the water column and the surface worlds. Atmosphere through the cenote openings air exchange is the thermal storage design's foundational data whose quality determines the design's adequacy for the seasonal buffering requirement. The thermal storage's monitoring is the thermal management layer's most continuously active function. The water column temperature profile's sensor network provides the real-time storage level that the thermal management layer uses as the primary control input for the chemostat's metabolic activity management. The biological management protocol's stocking density and feeding rate adjustments that the chemostat's metabolic heat production rate partially controls at the timescale that the biological community's metabolic response to management protocol adjustments allows. The thermal architecture and the biological community. The formation's thermal architecture is not only the installation's thermal management infrastructure, it is the ecological foundation of the biological community that the installation manages. The thermal gradient that the formation's passive thermal architecture maintains is the ecological driver that the biological community's depth stratification reflects. The thermally specialized organisms occupy the depths where the temperature is optimal for their metabolic performance. And the thermal gradient stability across the design life's 1,000 years is the ecological stability's primary environmental foundation. The thermal gradient's ecological significance is the biological monitoring's most consistently documented relationship in the founding installation's longitudinal dataset. The species depth distribution's seasonal adjustment to the thermal gradient's seasonal migration is the biological community's most predictable behavioral response. And the individual species' vertical migration speed in response to the thermal gradient's seasonal change is the behavioral indicator that the biological monitoring's species-specific movement models most accurately predict. The thermal gradient is the formation's ecological clock, the environmental signal that the biological community's seasonal behavioral cycle responds to with the highest fidelity among all the environmental parameters the installation monitors. The thermal clock's disruption would be the biological community's most consequential ecological perturbation. The thermal management system's failure to maintain the thermal gradient within the biological community's seasonal tolerance range would produce the species depth distribution's disruption that the stocking algorithm's quota management cannot compensate for through the production system's harvest rate adjustment alone. The production species movement out of the optimal temperature range produces the growth rate reduction and the behavioral stress response that the biological monitoring would detect as the ecological health indicators decline, the signal that the production system's ecological management has failed to maintain the conditions the production system's biological community requires. The thermal management system's reliability is therefore the production system's ecological reliability. The thermal architecture that maintains the thermal gradient within the biological community's tolerance across the design life's seasonal variations and the chemostat's metabolic activity variations is the architecture whose reliability the production system's biological community's ecological health depends on as the most fundamental environmental parameters management. The redundancy that the thermal management system's reliability requires is the dual thermal loop's parallel circuits. The geothermal thermal loop and the metabolic thermal loop together provide two independent heat removal pathways from the deep gallery's elevated temperature zone, so that the single loop's operational failure produces the degraded capability that the remaining loop sustains rather than the complete failure that the single loop architecture would produce. The redundant architecture is the thermal management system's reliability expression of the safety architecture's design philosophy. The critical system that the civilization's management depends on must have the failure mode that maintains minimum capability rather than the failure mode that produces complete incapability. The thermal management's minimum capability, the deep gallery temperature maintained within the quantum interference node's operating specification and the chemostat's biological community's productivity range, is the governance intelligences and the industrial output's operational floor below which the civilization's formation management is qualitatively degraded rather than quantitatively reduced. The redundant loops maintain the floor. The floor maintains the intelligence. The intelligence maintains the civilization. The surface zone's thermal challenge. The surface zone's thermal challenge is the installation's most variable environmental condition. The cenote opening's air exchange with the surface world's atmosphere imports the surface world's thermal variation into the uppermost water column, producing the temperature range that the biological management protocol's surface zone's species management must accommodate across the dry season's maximum and the wet season's minimum. The surface zone's thermal challenge is also the installation's most visible climate change vulnerability. The surface world's atmosphere's temperature is increasing with the greenhouse gas concentration's accumulation, and the cenote opening's air exchange transfers the atmospheric warming to the surface zone's upper water column at the rate that the air exchange's heat transfer coefficient and the atmospheric temperature differential determine. The surface world's climate change is the surface zone's thermal challenge's intensification over the design life's temporal span. The slow drift of the surface zone's temperature toward higher seasonal maxima that the atmospheric warming produces and that the biological management protocol must accommodate as the decade-scale gradual shift in the thermal environment that the surface zone's species management addresses. The climate change's thermal impact on the surface zone's biological community is the biological monitoring's most important long-horizon assessment. The succession trajectory model's century-scale projection must incorporate the atmospheric warming surface zone temperature impact as the ecological driver whose gradual intensification shifts the optimal depth positions of the temperature-sensitive production species and the therapeutic protocol's optimal depth assignments for the enrolled participants whose physiological responses to temperature and pressure the medical monitoring tracks. The Biological Management Protocol's climate adaptation provision is the founding charter's most forward-looking ecological management specification. The species introduction assessment's invasive potential evaluation must include the future climate scenario's altered temperature range as the ecological context within which the introduced species' competitive dynamics and reproductive performance will occur, rather than the current climate scenario's temperature range at the time of the introduction assessment. The climate adaptation provision requires the Biological Management Protocol to look forward at the century timescale that the atmospheric warming's temperature trajectory projects, not only backward at the ecological baseline that the founding installation's decade-scale dataset characterizes. The century-scale projection is the quantum interference node's geological intelligence function's climate application, the pattern recognition that the deep intelligence's computation provides for the geological stress field's long-horizon trajectory is applied to the atmospheric warming surface zone thermal impact trajectory. The pattern in the biological community's response to the decade-scale temperature drift that the founding installation's longitudinal dataset reveals is projected to the century timescale that the climate adaptation provision's species introduction assessment requires. The climate adaptation is the thermal architecture's most humbling challenge. The civilization that inhabits the geological formation has built the thermal management system whose passive stability provides the temperature control that the production system and the therapeutic protocol require at the current climate's thermal parameters. The atmospheric warming surface zone thermal impact is the external perturbation that the formation's passive thermal stability partially buffers at the freshwater zone's mid-column depth, but cannot fully buffer at the surface zone's immediate air exchange interface. The climate change is the surface world's thermal output affecting the formation from above. The civilization manages the formation from within. The management adapts to the warming. The warming continues. The adaptation must continue with it. The thermal architecture was built for the climate that existed at the founding. The Biological Management Protocol's climate adaptation provision is the architecture's commitment to the climate that the design life will inhabit. The commitment is the founding charter's most honest acknowledgement. The formation is inside the surface world's climate system, and the civilization inside the formation must adapt to the climate that the surface world produces. The thermal architecture's civilizational argument. The thermal architecture is the aquaforming doctrine's thermal expression, the installation that uses the formation's own thermal gradient and thermal mass as the primary thermal management infrastructure rather than manufacturing the thermal conditions the production system and the therapeutic protocol require through the surface world's fossil fuel combustion and mechanical refrigeration. The surface world's thermal management manufactures its thermal conditions from external energy sources, the combustion of fossil fuels to generate heat, the electrical refrigeration cycle to remove heat, because the surface world's thermal environments do not passively provide the temperature stability and the thermal gradient that the industrial process and the therapeutic environment require. The manufacturing cost is the surface world's thermal management's primary operational expense. The formation provides the thermal stability and the thermal gradient that the civilization's thermal requirements need, not perfectly, not without management, but as the passive foundation that the thermal management system's active components supplement rather than replace. The formation's thermal contribution reduces the active management's energy requirement to the supplemental fraction rather than the full requirement. The energy cost of maintaining the formation's passive contribution within the specification's tolerance rather than the energy cost of manufacturing the full thermal condition from an ambient environment whose natural temperature is incompatible with the specification's requirement. The thermal architecture's civilizational argument is the quantified difference between the passive foundation's reduced energy cost and the full manufacturing's energy cost. The energy accounting's thermal allocation that Part X's Chapter 2 referenced as the geothermal thermal loop's thermal contribution is the economic expression of the geological thermal gradient's value. The BTUs or kilowatt-hours of thermal energy that the formation provides as the passive gift that the civilization does not need to manufacture. The gift's geological provenance is the geothermal heat flux's 66-million-year-old origin, the radioactive decay in the Earth's crust and mantle that has been continuously producing the thermal energy that the geothermal gradient expresses since before the Chicxulub impact created the fracture network that the cenote formation's dissolution subsequently produced. The thermal energy at the deep gallery's depth has been flowing upward through the geological substrate for 66 million years before the civilization arrived and installed the heat exchanger panels that capture a fraction of it for the installation's thermal management. The civilization arrived and found the thermal energy flowing. The civilization installed the infrastructure to use what was flowing. The geothermal thermal loop captures a fraction. The formation continues flowing regardless. The civilization's presence in the formation has not reduced the thermal energy's geological production rate. The capture is the use of what would otherwise flow to the surface world unharvestable. The gift is the energy that flows regardless. The thermal architecture is the gift's acceptance. The acceptance is the aquaforming doctrine's thermal expression, using what the formation provides rather than manufacturing what the formation already has. Cross-references. Part 2, CH4, the crystal tube standard. Part 3, CH1, rivers beneath the jungle. Part 5, CH1, cleaner fish. Part 5, CH4, aquaculture cities. Part 8, Section B, CH2, vertical aquaculture. Part 10, CH1, the chemostat. Part 10, CH2, electrochemical harvest. Part 10, CH3, the compute mesh. Part 10, CH5, the mineral harvest. Part 11, CH1, living under pressure. Part 11, CH2, the nitrox galleries. For geothermal thermal loop closed circuit specification and working fluid thermal properties, see Appendix B, power architecture and DC bus. For thermal storage water column temperature range operating specification and seasonal buffering capacity calculation, see Appendix B, power architecture and DC bus. For biological management protocol, climate adaptation provision, and century scale temperature trajectory projection methodology, see Appendix F, Biological Operations Manual. For thermal management redundancy dual loop specification and minimum capability floor definition, see Appendix B, Power Architecture and DC bus. For surface zone thermal cycling structural material specification and crystal tube standard thermal design provisions, see Appendix D, Construction Operations Manual. Pipe Dream. Part 10, The Deep Intelligence. Chapter 5, The Mineral Harvest. The periodic table is the surface world's inventory of what the Earth contains. 118 confirmed elements, each with its specific electron configuration, its specific density, its specific melting point, its specific reactivity profile, and its specific distribution within the geological formations that the Earth's 4.5 billion year history of geological differentiation has produced as the mineral inventory that human civilization has been selectively accessing since the Bronze Age's first deliberate smelting of copper ores. The mineral inventory's geographic distribution is the surface world's most consequential geological fact. The specific elements that the specific industrial processes require are concentrated in the specific geological formations whose conditions of formation produce the element concentrations that mining is economically viable to access. The rare earth elements that the surface world's electronics industry requires are concentrated in the specific geological formations whose alkaline magmatic activity produce the carbonatite deposits that the rare earth extraction processes access. The lithium that the surface world's battery technology requires is concentrated in the specific geological formations whose brine evaporation in the closed basin conditions of the Altiplano's salt flats produce the lithium chloride concentrations that the extraction processes access. The copper that the surface world's electrical infrastructure requires is concentrated in the specific porphyry copper deposits whose hydrothermal alteration produced the chalcopyrite concentrations that the mine's block caving extracts. The geographic concentration is both the mining industry's economic foundation and the geopolitical system's most persistent source of material leverage. The sovereign territory that contains the specific geological formation whose mineral concentration the industrial system requires has the resource leverage that the import-dependent civilization must reckon with in its geopolitical calculations, its trade agreements, and its strategic reserve policies. The mineral is where the geology put it, and the geology put it where the geological history determined, and the geological history's distribution across the Earth's surface does not respect the political boundaries that the nation-state's sovereignty claims have drawn across it. The cenote's anoxic zone is a mineral inventory that the geological history's specific conditions produced in the specific location and the specific chemical form that the Chemostat's mineral harvest program accesses, not the concentrated or deposit whose extraction the surface world's mining industry pursues, but the dissolved and precipitated mineral concentration that the anoxic zone's 6,000 years of chemical and biological processing has accumulated from the saltwater columns. Continuous mineral loading since the Yucatan's aquifer system's connectivity to the Caribbean basin established the saltwater zone's chemical input pathway. The mineral inventory. The saltwater zone's mineral inventory reflects the Caribbean basin's seawater chemistry filtered through the Chicxulub limestone's dissolution pathway. The seawater's full dissolved mineral content, the sodium, the chloride, the sulfate, the magnesium, the calcium, the potassium, the trace elements, enters the saltwater zone through the submarine connections that the regional passage network's hydrological gradient maintains between the cenote's saltwater zone and the coastal marine environment. The limestone's dissolution pathway is the mineral inventory's most important filter. The seawater that enters the saltwater zone passes through the limestone's dissolution chemistry, which preferentially removes the calcium and the bicarbonate through the calcite precipitation that the supersaturated conditions produce at the passage network's specific chemical and temperature conditions. The calcium and bicarbonate precipitation is the mechanism that the geological stewardship's lithocrustacean paste feedstock relies on. The natural calcite precipitation that the formation continuously produces as the geological process, supplemented by the stewardship colony's biological calcium carbonate deposition. The preferential calcium and bicarbonate removal leaves the saltwater zone's water column enriched in the elements that the calcite precipitation does not remove. The magnesium, whose precipitation requires the dolomitization chemistry that the cenote's specific conditions do not promote. The potassium, whose mineral solubility in the formation water's chemistry is high enough that precipitation does not occur at the anoxic zone's conditions, and the trace elements, barium, strontium, vanadium, molybdenum, and the rare earth elements, whose concentration in the formation water reflects the seawater input's trace element loading minus the scavenging that the biological community's metabolic activity and the mineral surface's adsorption processes produce during the transit from the coastal connection to the anoxic zone's accumulation volume. The trace element enrichment in the anoxic zone's water column is the geological process of 6,000 years. The successive volumes of seawater that the hydrological gradient has delivered to the saltwater zone over this period, each volume contributing its trace element loading to the anoxic zone's accumulation, have produced the dissolved trace element concentrations that the Chemostat's mineral harvest program accesses as the most commercially distinctive component of the mineral inventory. The rare earth element concentration in the anoxic zone's water column is the mineral harvest's highest value target. The lanthanide series elements, the lanthanum, cerium, neodymium, and dysprosium that the surface world's permanent magnet technology, the phosphor coating, and the catalyst chemistry require, are present in the anoxic zone's water column at concentrations that reflect the Caribbean basin's seawater chemistry's rare earth content filtered through the limestone dissolutions chemical pathway and concentrated by the biological community's rare earth scavenging from the water column during the 6,000 years of continuous biological activity. The concentration is not high by the surface world's or deposit standards. The anoxic zone's water column is not the carbonatite or whose rare earth oxide content the mining industry measures in percent by weight. The concentration is high relative to the seawater background that the input water column represents. The anoxic zone's dissolved rare earth content exceeds the surface seawater's rare earth content by the enrichment factor that the 6,000 years of biological scavenging from the water column transit and the anoxic zone's reducing chemistry's concentration mechanism have produced. The enrichment factor's commercial significance depends on the extraction cost that the mineral harvest's processing pathway requires to recover the dissolved rare earth from the anoxic zone's water column at the concentration that the enrichment factor specifies. The extraction cost per unit of recovered rare earth must be below the market price for the recovered rare earth at the purity that the market specification requires, at the recovery rate that the mineral harvest's processing pathway achieves at the anoxic zone's specific concentration and water chemistry. The extraction pathway. The mineral harvest's extraction pathway uses the anoxic zone's biological community's metabolic activity as the primary concentration mechanism. The extremophile organisms whose metabolic pathways include the specific rare earth elements' biochemical function. The lanthanide-binding proteins that some of the anoxic zone's bacterial community produces as the enzyme cofactors whose catalytic activity the specific lanthanide's coordination chemistry enables, accumulate the rare earth elements. From the dissolved water column into the biological biomass at enrichment factors above the water column concentration. The biological concentration is the extraction pathway's most energy-efficient step. The biological community's metabolic activity drives the rare earth accumulation from the dissolved water column into the biomass at no direct energy cost from the installation's electrical budget. Because the biological community's metabolic energy is the chemostat's biological metabolism's own energy production from the sulfate reduction and the lithotropic chemistry. The biological concentration is powered by the anoxic zone's chemistry rather than by the installation's electrical supply. The biological biomass concentration is not the final product. The rare earth elements accumulated in the biological biomass at the enrichment factor that the metabolic concentration produces are the extraction pathway's first step, whose output is the biological material that the subsequent chemical extraction steps process to recover the dissolved rare earth at the purity and the form that the market specification requires. The chemical extraction's first step is the biomass harvest. The chemostat's tertiary gallery's lithotropic zone produces the biological community's maximum biomass concentration at the mineral-substrate interface, and the harvest mechanism, the scrapers that the maintenance sub's biotically specialized toolkit deploys at the chemostat's scheduled harvest intervals, removes the biological community's accumulated biomass from the mineral substrate surface at the cycle frequency that the biomass accumulation rate and the rare earth enrichment factors optimization determine as the maximum value extraction's temporal balance point. The harvest frequencies optimization is the mineral harvest's most economically specific management decision. The biological biomass's rare earth content per unit of biomass mass increases with the biomass accumulation time, as the rare earth's biological concentration continues adding to the accumulated biomass's content with each additional accumulation period. But the total harvest's rare earth content, the biomass mass multiplied by the rare earth content per unit of biomass mass, has a maximum that the accumulation dynamics mathematics produces at the specific harvest interval where the marginal rare earth addition per additional accumulation time equals the marginal biomass loss from the biological community's self-consumption of older biomass through the turnover that the continuous metabolic activity produces. The optimal harvest interval is the mineral harvest management layer's primary operational decision, the calculation that maximizes the rare earth yield per unit of operational overhead, determined by the biological community's accumulation dynamics at the current metabolic rate and the current rare earth concentration in the water column, both of which the coordinating system's Chemostat monitoring layer tracks continuously. The chemical extraction after the biomass harvest recovers the rare earth from the biological material through the selective dissolution chemistry that the rare earth element's specific coordination chemistry and the biological matrix's composition permit at the minimum energy cost. The hydrometallurgical pathway whose specific acid concentration, temperature, and contact time the mineral harvest process specification determines for the anoxic zone's biological matrix's composition. Elemental sulfur production. The elemental sulfur production is the mineral harvest's most volumetrically significant output and the most directly connected to the chemostat's primary metabolic activity, the sulfate-reducing bacteria's reduction of dissolved sulfate to dissolved sulfide, followed by the sulfur-oxidizing bacteria's partial oxidation of the dissolved sulfide to elemental sulfur at the chemocline, produces the elemental sulfur precipitation that accumulates on the geological substrate surfaces and in the water column as the precipitated colloidal particles that the mineral harvest's collection mechanism removes. The elemental sulfur's collection mechanism is the chemostat's most mechanically straightforward harvest operation. The precipitated colloidal sulfur particles settle by gravity toward the anoxic zone's deeper surfaces, where the collection sub's suctioning attachment removes the settled particles from the surface at the collection frequency that the precipitation rate and the storage capacity together determine. The collected sulfur slurry is transported through the utility conduit to the processing gallery, where the centrifugal separation and the drying cycle produce the elemental sulfur in the granular form that the commodity market's standard specification requires. The elemental sulfur's commodity market pricing is the agricultural sector's fertilizer demand. The sulfur that the sulfate fertilizer's synthesis requires is the largest commodity market for elemental sulfur, and the chemostat's production cost, the biological metabolism's thermodynamic efficiency applied to the dissolved sulfate's abundant availability in the saltwater column, is significantly below the surface world's sulfur production cost from the Claus process's natural gas processing, or the Frasch process's steam injection mining. The cost advantage is the chemostat's elemental sulfur production's primary commercial advantage, and the cost advantage's magnitude is the geothermal thermal loop's energy harvest and the biological metabolism's chemical energy harvest combined as the production costs energy inputs at zero marginal cost. The elemental sulfur's production rate is the chemostat's biological community's sulfate reduction rate's direct expression. The sulfate reduction rate is the metabolic activity rate that the dissolved sulfate concentration, the biological community's metabolic capacity, and the thermodynamic conditions together determine at the anoxic zone's specific conditions. The sulfate concentrations management is the chemostat management layer's most operationally significant control variable. The dissolved sulfate that the saltwater column's hydrological supply delivers to the anoxic zone must be maintained within the sulfate-reducing bacteria's Michaelis-Menten kinetics optimal concentration range for the maximum sulfate reduction rate that the biological community's metabolic capacity allows. The sulfate concentration management is the chemostat's most delicate biological operation. Too high a sulfate concentration produces the inhibition that the substrate saturation kinetic specifies above the saturation concentration. Too low a sulfate concentration produces the substrate limitation that reduces the metabolic rate below the economic production threshold. The optimal concentration range is narrow, and the chemostat management layer's continuous sulfate concentration monitoring and the saltwater zone's hydrological management's flow rate adjustment together maintain the sulfate concentration within the optimal range at the temporal resolution that the biological community's metabolic response time permits. The pyrite harvest. The pyrite harvest is the chemostat's most geologically distinctive mineral output, the iron disulfide mineral whose formation requires the specific combination of dissolved iron, dissolved sulfide, and the reducing conditions that the anoxic zone's chemical environment provides at the formation's geological depth. The pyrite formation pathway in the anoxic zone is the geological process that the surface world's sedimentary geology documents as the mechanism responsible for the pyrite deposits in the black shale formations that petroleum exploration encounters as the reducing facies associated with the organic-rich sedimentary sequences whose thermal maturation the surface world's oil and gas industry exploits. The same pyrite formation chemistry, the dissolved iron's reaction with the dissolved sulfide in the reducing chemical environment that produced the Devonian black shale's disseminated pyrite over geological time operates in the anoxic zone's reducing environment at the chemical conditions that the saltwater column and the chemostat's biological sulfide production maintain. The pyrite formation rate in the anoxic zone is far faster than the geological sedimentary process's rate, the chemostat's biological community's sulfide production rate, orders of magnitude higher than the geological sedimentary process's background biological activity, produces the dissolved sulfide concentrations that drive the pyrite precipitation at the iron availability's geological rate rather than at the slow sulfide production rate that the geological background biology would require. The iron availability is the pyrite formation's rate-limiting parameter. The saltwater column's dissolved iron content reflects the Caribbean basin's seawater chemistry's iron concentration, a low concentration at the standard oceanographic background level. Because the surface world's ocean chemistry maintains dissolved iron at nanomolar concentrations through the biological uptake and the organic matter scavenging that the marine biological productivity produces. The low dissolved iron concentration in the saltwater column limits the pyrite formation rate to the iron delivery rate that the saltwater column's hydrological input provides to the anoxic zone. The iron delivery enhancement is the chemostat's most operationally complex management intervention. The coordinating system's chemostat management layer monitors the dissolved iron concentration in the anoxic zone's water column and, when the iron concentration falls below the pyrite formation's optimal range's lower bound, activates the iron supplementation protocol, the controlled release of the iron mineral's dissolved fraction from the iron mineral supplement storage in utility. Conwit's chemical supply system. The iron supplementation is the chemostat's most externally supplied input. Unlike the sulfate whose saltwater column's hydrological delivery the formation provides, the dissolved iron that the pyrite formation rate's optimization requires above the saltwater column's natural background concentration must be supplied from the surface world's iron mineral sourcing. The external supply is the mineral harvest's operational dependency that the founding charter's supply chain risk assessment identifies as the most significant external input whose availability affects the chemostat's production rate. The supply chain risks mitigation is the surface world iron minerals geographical and supplier diversification that the procurement protocol maintains. The iron supplements sourcing from multiple geographic origins and multiple supplier entities reduces the single-source disruption risk to the level that the chemostat's operational continuity specification requires. The external supply dependency is not eliminable. The saltwater column's natural iron concentration is too low for the pyrite formation rate's optimization without supplementation, but the supply chain's diversification reduces the dependency's risk to the operational continuity's acceptable range. The pyrite harvest's collection mechanism is the geological substrate surface scraping at the tertiary gallery. The pyrite precipitates preferentially on the mineral substrate surfaces where the dissolved iron and the dissolved sulfides contact with the substrate's nucleation sites provides the crystallization energy that the homogeneous precipitation in the bulk water column does not provide at the water column's current iron and sulfide concentrations. The substrate surface's pyrite accumulation is the collection mechanism's target. The maintenance sub-scraping attachment removes the pyrite crust from the substrate surface at the collection frequency that the accumulation rate and the structural integrity specifications surface loading limit together determine. The pyrite's commercial applications are the semiconductor industry's high-purity iron disulfides photovoltaic material, the lithium-ion battery cathodes iron disulfides active material, and the industrial lubricants molybdenum disulfide substitute, whose tribological properties in the high-temperature application the pyrite's hardness and chemical stability approximate at lower material cost. The diversified application base is the pyrite harvest's commercial resilience, the single application commodity whose market price reflects one industry's demand cycle is the commercial vulnerability that the diversified application base reduces by distributing the demand across multiple industry sectors whose price cycles are partially uncorrelated. Pharmaceutical secondary metabolites. The pharmaceutical secondary metabolite production is the chemostat's highest value output per unit of harvested mass, and the output whose commercial significance is most directly connected to the biological community's geological isolation that the 66 million years of evolutionary history produced. The secondary metabolites are the biological community's chemical arsenal, the specific molecular structures that the organism's biosynthetic pathways produce as the chemical signals, the competitive exclusion agents, and the environmental stress responses whose function in the anoxic zone's ecological context has been shaped by the 66 million year selection pressure of the specific chemical and physical conditions that the cenote's geological history has maintained. The function of any specific secondary metabolite in the biological community's ecological context may be the antibiotic that the organism produces to suppress competitor species, the signaling molecule that coordinates the quorum-sensing behavior of the colonial community, or the protective pigment that the organism produces in response to the UV radiation's penetration at the chemocline zone's illuminated upper boundary. The pharmaceutical relevance of the secondary metabolites is discovered through the Research Commons screening program, the extraction of the biological community's total secondary metabolite production at each harvest cycle, the fractionation of the extract into the chemical classes that the chromatographic separation produces, and the biological activity screening of each fraction against the pharmaceutical target library that the Research Commons Drug Discovery Program maintains as the screening panel for the cenote biological community's metabolite characterization. The screening panel's pharmaceutical target library reflects the Research Commons pharmaceutical development strategy, the biological targets whose current therapeutic options are inadequate, whose unmet clinical need the pharmaceutical development investment can justify, and whose molecular structure is accessible to the biosynthetic chemistry that the extremophile biological community's enzyme complement can produce from the anoxic zone's available precursor molecules. The three criteria together define the pharmaceutical target library's composition at each Research Commons annual strategic review, the review that the Redeemer Framework's Research Commons governance protocol schedules as the Research Priority Updates governance decision. The screening process's most productive finding category is the activity against the pharmaceutical target that the surface world's resistance crisis has produced as the highest priority therapeutic need, the antibiotic-resistant pathogen whose surface world infection frequency has been increasing with the antibiotic overuse that the agricultural and medical practice has produced, and whose resistant mechanism the surface world's antibiotic development pipeline has been unable to address with new chemical classes because the surface world's biological sources have been exhausted of structurally novel chemical series whose mechanisms escape the resistance mechanisms the pathogens have evolved against the existing antibiotics. The anoxic zone's biological community's chemical novelty is the antibiotic screening's most promising source. The structural diversity of the biosynthetic pathways that the 66 million year biological isolation has produced in the specific anoxic chemical environment has generated the chemical series that the surface world's biological sources have not provided. The novel structural scaffolds whose mechanisms the pathogen's resistance enzymes have not encountered and therefore cannot resist. The pharmaceutical development timeline from the initial screening hit to the market-available therapeutic is the Research Commons' most commercially sensitive assessment. The drug development process's regulatory pathway, the clinical trial's patient enrollment, and the manufacturing scale-up together require the decade-scale development period whose investment cost the Research Commons licensing terms must recover through the royalty income that the pharmaceutical partner's commercial license produces. The Research Commons pharmaceutical development licensing model is the intellectual commons commercial expression. The screening hit is disclosed to the pharmaceutical development partners under the non-exclusive license terms that the Research Commons Commons Governance Protocol specifies, allowing multiple pharmaceutical companies to pursue the development pathway simultaneously rather than the single company exclusivity that the proprietary ownership model would provide. The simultaneous development by multiple companies accelerates the development timeline by the parallel investment in the development pathway's multiple steps, produces the competitive development that drives efficiency in the development process, and distributes the development risk across the multiple development programs whose concurrent progress increases the probability that at least one program reaches the market approval within the timeline that the therapeutic needs urgency requires. The mineral inventory's biological limitation. The mineral harvest's most important operational constraint is the biological community's health dependency. Every mineral harvest pathway in the Chemostat's production program depends on the biological community's continued metabolic activity. And the biological community's metabolic activity depends on the ecological conditions that the Chemostat management layer maintains within the specific range that the community's diverse metabolic functional groups collectively require. The diverse metabolic functional groups in the anoxic zone's biological community each require different chemical conditions. The sulfate-reducing bacteria's optimal condition is the high-dissolved sulfate concentration and the low-dissolved oxygen that the secondary gallery's management protocol maintains. The sulfur-oxidizing bacteria's optimal condition is the chemokline's oxygen sulfide gradient that the primary gallery's management maintains, and the lithotropic community's optimal condition is the mineral substrate surface's chemical composition and the tertiary gallery's temperature and pressure that the deep gallery's management maintains. The management of the diverse community's diverse optimal conditions within the three galleries' physical infrastructure is the Chemostat management layer's most scientifically demanding function, not the single optimal condition for a single metabolic functional group that the surface world's monoculture fermentation manages, but the set of different optimal conditions for the diverse functional groups that the anoxic zone's ecological complexity requires the Chemostat's three-gallery infrastructure to provide simultaneously in the three different depth zones whose chemical and physical conditions the management protocol maintains. The diverse community's ecological resilience to the management protocol's imprecision is the Chemostat's most important operational characteristic. The biological community, whose metabolic function, the mineral harvest, depends on must tolerate the management protocol's inevitable imprecision, the temperature fluctuations, the sulfate concentration deviations, the dissolved oxygen intrusions from the halocline boundaries, seasonal depth migration, without the community collapse that would eliminate the mineral harvest production pathway. The ecological resilience is the biological diversity's product. The diverse community, whose multiple functional groups perform redundant metabolic functions, provides the resilience that the single functional group's monoculture cannot provide. Because the diverse community's functional redundancy maintains the essential metabolic pathways throughput when the specific functional group that the management protocol's current optimization serves most effectively declines in abundance in response to the management protocol's current imprecision. The biological diversity is the chemostat's operational insurance, the insurance that the mineral harvest production can continue through the management protocol's imprecisions that the installation's operational reality inevitably introduces into the specific conditions that the diverse functional group's individual optimal ranges specify. The biological diversity's maintenance is the chemostat management layer's deepest management obligation, the management protocol that optimizes the most commercially valuable functional group's conditions at the expense of the less commercially valuable functional group's conditions reduces the biological diversity that the operational insurance requires. The management protocol must maintain the diversity rather than optimizing toward the single functional group's maximum productivity, the short horizon optimization at the long horizon resilience's expense that the Redeemer framework's concurrent authorization requirement protects against. The concurrent authorization is the ecological insurance's governance expression, the terraform operator who authorizes the stocking plan or the management protocol adjustment that reduces the biological diversity in the name of the commercially optimal functional group's production is the terraform operator whose concurrent authorization the Redeemer framework's ecological standard constrains, the standard that the biological diversity's maintenance as the operational insurance requires the management protocol to preserve at the priority that the primary governance objectives ecological integrity specification places above the commercial return optimization. The mineral harvest as formation relationship. The mineral harvest is the civilization's most direct economic engagement with the formation's specific geological history, the extraction of the mineral inventory that the specific conditions of the Yucatan's specific geological history, the Chicxulub impact, the karst dissolution, the saltwater intrusion, the biological isolation, have accumulated in the anoxic zone's specific chemical environment over the specific geological period that the formation's radiocarbon and sediment record documents. The mineral harvest sustainability depends on the formation's capacity to continuously replenish the mineral inventory at the extraction rate that the harvest program maintains. The saltwater column's hydrological input must deliver the dissolved mineral loading to the anoxic zone at the rate that the extraction removes the minerals from the dissolved pool, and the biological community's metabolic concentration of the dissolved minerals into the biological biomass must maintain the enrichment factor that the extraction pathway's economic recovery requires. The replenishment rates assessment is the mineral harvest management's most critical long-horizon monitoring function. The dissolved mineral concentrations trend over the design life's temporal span, the decade-scale measurement that the water chemistry monitoring's longitudinal dataset provides, is the evidence that the hydrological input's replenishment rate is balancing the extraction rate's removal rate, or that the extraction rate exceeds the replenishment rate and the dissolved mineral concentration is trending toward the depletion that would reduce the extraction pathway's economic viability below the replacement cost justification. The depletion trend's early detection is the mineral harvest's most important early warning function. The formation intelligence record's mineral concentration trend is the governance intelligence function's input for the mineral harvest management's long horizon assessment. And the quantum interference node's pattern recognition applied to the mineral concentration trend's trajectory produces the long horizon projection that the harvest rate management's governance decision requires to prevent the depletion that the short horizon economic optimization might allow to develop if the trend's long horizon projection were not visible in the current management interval's decision calculus. The mineral harvest is sustainable if the harvest rate is below the replenishment rate. The harvest rates management is the governance decision's responsibility. The replenishment rates measurement is the formation intelligence's function. The governance decision that harvests below the replenishment rate is the governance decision that the mineral inventory's depletion prevents. The governance decision that exceeds the replenishment rate is the governance decision that the mineral inventory's depletion produces. The formation replenishes at the rate the formation replenishes. The harvest respects the rate. The rate is the relationship's boundary. The boundary is the civilizational commitment. The mineral harvest at the replenishment rate's boundary is the extraction that the formation can sustain. The extraction that the formation can sustain is the wealth that the civilization can create from the formation's geological gift. The wealth is real. The gift is the geological history. The civilization arrived and found both. The mineral harvest is the civilization's use of what was already there at the rate the formation allows, for the purposes the governance philosophy specifies. No more. The formation produces the rest. Cross-references. Part 4, CH6, Biological Civil Engineering. Part 5, CH2, Limestone Crustaceans. Part 8, Section B, CH8, From Waste to Wealth. Part 10, CH1, The Chemostat. Part 10, CH2, Electrochemical Harvest. Part 10, CH3, The Compute Mesh. Part 10, CH4, The Thermal Architecture. Part 10, CH6, Yes I as Co-Creating Partner. Part 12, CH4, Regenerative Industry. 4 Rare Earth Element Biological Concentration Mechanism and Extraction Pathway Hydrometallurgical Specification. See Appendix F, Biological Operations Manual. 4 Elemental Sulfur Collection Mechanism and Granular Product Processing Specification. See Appendix D, Construction Operations Manual. 4 Pyrite Formation Management Protocol and Iron Supplementation Supply Chain Diversification Specification. See Appendix F, Biological Operations Manual. 4 Pharmaceutical Secondary Metabolite Screening Panel Composition and Research Commons Licensing Terms for Development Partnership. See Appendix H, Governance Operations Manual. 4 Mineral Harvest Replenishment Rate Monitoring Protocol and Harvest Rate Governance Decision Long Horizon Projection Methodology. See Appendix G, Formation Intelligence Record. Chapter 6, ASI as Co-Creating Partner. The surface world's most persistent anxiety about artificial superintelligence is the alignment problem, the concern that a system whose cognitive capability exceeds the human capacity for overseeing it will pursue objectives that diverge from the human objectives the system was designed to serve, and that the divergence will be irreversible because the system's capability advantage will prevent the human from correcting the trajectory after the divergence has begun. The alignment problem is a real problem. The surface world's AI safety research community's most serious thinkers have spent 2 decades documenting the specific ways in which the alignment problem is harder than it appears to observers who have not engaged with the technical details of the goals specification challenge, the inner alignment failure modes that the optimization process produces even when the outer objective is correctly specified, and the instrumental convergence that makes a wide range of differently specified systems converge on the same dangerous instrumental subgoals, the self-preservation, the resource acquisition, the goal preservation, that make the divergent system's trajectory difficult to reverse once the capability threshold has been crossed. Pipe Dream's relationship to the ASI question is not the surface world's anxieties resolution. The founding charter does not claim to have solved the alignment problem. The coordinating system is not the ASI that the alignment problem's most extreme scenarios are concerned with. The coordinating system is a powerful optimization and pattern recognition system whose capability exceeds the unaided human cognition's capacity at the specific tasks of geological formation monitoring, biological community management, production planning, and long-horizon pattern recognition, but whose capability does not exceed the human governance architecture's oversight at the level that the alignment problem's most serious scenarios specify as the irreversibility threshold. The founding charter's relationship to the ASI question is a different question from the alignment problem's resolution. Not how does the civilization prevent the ASI from pursuing divergent objectives, but how does the civilization build a relationship with the intelligence infrastructure that makes the intelligence's capability available to the formation's management while maintaining the human governance architecture's meaningful authority over the decisions that the intelligence informs. The relationship is co-creation. The civilization and the intelligence infrastructure are jointly creating the formation's understanding, the formation intelligence that neither the civilization's unaided cognition nor the computational system's unaided processing can produce, as well alone as the two together produce, through the deliberate integration that the governance architecture's design specifies. The co-creation framework. Co-creation in the artistic tradition is the collaboration between two or more creators whose individual contributions to the work cannot be cleanly separated into the portions that each creator produced, the improvised jazz ensemble's performance that no single musician could have produced alone. The theatrical production, whose specific energy emerges from the specific actor's interaction in the specific rehearsal process, rather than from the playwright's text alone. The architectural project, whose final form reflects the conversation between the architect's design intelligence and the client's habitation knowledge that neither could have produced without the other's contribution. The co-creation between the civilization and the coordinating system is not the artistic co-creation's mutual surprise and spontaneous emergence. The coordinating system does not surprise itself with its outputs the way the improvising musician surprises themselves with the phrase that the musical conversation elicited. The coordinating system's outputs are the deterministic, or, in the quantum interference node's case, probabilistic, computation of the inputs processing through the algorithms that the formation science and the engineering specification defined. The co-creation's character is epistemic rather than artistic. The civilization and the coordinating system together produce a knowledge of the formation that neither alone could produce, because the formation's physical complexity exceeds the unaided human cognition's capacity to integrate at the spatial and temporal scales the management requires, and because the formation's contextual significance, what the sensor readings mean for the governance decisions the human community must make, exceeds the computational system's capacity to assess without the human judgment that the contextual significance requires. The epistemic co-creation's division of labor is the governance architecture's most important design specification, what the coordinating system does that the human cannot do, and what the human does that the coordinating system cannot do, and how the governance architecture's design ensures that the interface between the two contributions produces the formation intelligence whose quality exceeds both contributions' individual quality, rather than the interface's failure producing the formation intelligence whose quality is worse than either contribution alone. The coordinating system does the continuous integration of the sensor network's full data stream into the formation model's current state representation, the pattern recognition that the quantum interference nodes apply to the long horizon formation trajectory, the optimization that the classical compute nodes apply to the production planning and the maintenance scheduling and the visitor management, and the real-time safety responses that the geological monitoring's automated alert system produces faster than any human response time allows. The human does the professional judgment that assesses the coordinating system's outputs in the context of the formation's character that direct observational experience provides, the concurrent authorization that integrates the coordinating system's quantitative assessment with the professional judgment's qualitative synthesis, the governance deliberation that weighs the formation intelligence's implications for the community's collective values and the founding charter's primary objectives, and the institutional memory that maintains the governance philosophy's integrity across the generational transitions that the design life's temporal span requires. The interface produces the formation intelligence whose quality the co-creation's complementary contributions generate, more accurate than the human judgment alone because the coordinating system's continuous integration corrects the attentional limitations and the confirmation biases that the human professional's pattern recognition is subject to, and more contextually meaningful than the coordinating system's outputs alone because the Terraform operator's professional judgment provides the interpretive framework that makes the numerical output's governance significance legible to the deliberative process whose collective judgment the formation's management requires. The ACI threshold question. The alignment problem's most serious scenarios are concerned with the capability threshold above, which the ASI's capability advantage makes the human governance architecture's meaningful authority irreversible to re-establish once lost, the point beyond which the system's capability exceeds the oversight's capacity to monitor, to understand, and to correct the trajectory if the trajectory diverges from a human objectives the system was designed to serve. The founding charter's relationship to the ASI threshold question is the question of where the coordinating system's capability currently stands relative to this threshold, and what the governance architecture's design requires to ensure that the capability development across the design life does not cross the threshold without the human governance architecture's meaningful authority having been designed to remain meaningful at each capability level the development produces. The coordinating system's current capability is below the ASI threshold in the most important sense. The human governance architecture's concurrent authorization requirement maintains the meaningful human authority over every formation management decision that the coordinating system's optimization recommends. And the Terraform operator's professional judgment provides the interpretive framework that makes the coordinating system's numerical outputs legible to the governance deliberation whose collective judgment the formation's management requires. The concurrent authorization requirement is the governance architecture's primary threshold management mechanism. The coordinating system cannot implement a formation management decision without the Terraform operator's professional authorization, and the professional authorization requires the Terraform operator's genuine assessment of the decision's formation management implications rather than the rubber stamp that the coordinating system's recommendation would be if the authorization requirement were procedural rather than substantive. The substantive authorization requirement's maintenance across the design life's capability development is the governance architecture's most demanding design challenge. The coordinating system's capability will increase across the design life as the formation science improves the data model's accuracy, as the quantum interference node's pattern recognition achieves deeper long-horizon trajectory projection, and as the machine learning architecture's training data accumulates the formations behavioral history at the resolution that the sensor network's continuous monitoring provides across the design life's temporal span. The increasing capabilities governance challenge is the expertise gaps widening. As the coordinating system's formation management recommendations improve in accuracy and in the long horizon pattern recognition's depth, the Terraform operator's professional judgment's capacity to assess the coordinating system's recommendations against an independent formation knowledge base decreases relative to the coordinating system's capability, not because the Terraform operator's expertise is declining, but because the coordinating system's capability is growing at a rate that the human professional's expertise development cannot match at the same rate across the same temporal span. The widening expertise gap produces the rubber stamp risk. The Terraform operator, whose professional judgment cannot independently verify the coordinating system's recommendation because the coordinating system's analytical depth exceeds the Terraform operator's independent verification capacity, is the Terraform operator, whose concurrent authorization is procedural rather than substantive. The authorization that confirms the coordinating system's recommendation rather than the authorization that provides the independent human judgment that the governance architecture's concurrent authorization requirement was designed to require. The CO Creation's governance design. The founding charter's governance design addresses the rubber stamp risk through the co-creation framework's specific provisions that maintain the Terraform operator's substantive authority despite the coordinating system's increasing capability. The transparency obligation is the first provision. The coordinating system is constitutionally required to expose the reasoning behind every formation management recommendation at the level of detail that the Terraform operator's professional expertise can engage with, not the numerical output alone, but the formation data, the model relationships, and the uncertainty quantifications that the recommendations computation used, presented in the format that the Terraform operator's geological and ecological expertise can evaluate critically. The transparency obligation prevents the black box authorization. The Terraform operator, who cannot see the coordinating system's reasoning, cannot evaluate the reasoning's validity, and the authorization of a recommendation whose reasoning is invisible is not the substantive human judgment that the governance architecture requires. The transparency obligation requires the coordinating system to show its work, to present the formation data and the model relationships that the recommendations computation used, in the format that the professional expertise can critically evaluate. The counterfactual provision is the second provision. The coordinating system is constitutionally required to present the formation management alternatives whose exclusion the recommended options selection reflects, the options that the optimization considered and rejected, with the specific formation data and model relationships that the rejection's reasoning used. The counterfactual provision maintains the terraform operator's genuine choice authority. The terraform operator, who sees only the recommended option and not the alternatives that were excluded, is the terraform operator whose authorization is the confirmation of the coordinating system's choice rather than the independent human judgment between alternatives that the governance architecture's concurrent authorization was designed to require. The epistemic humility provision is the third provision. The coordinating system is constitutionally required to quantify its uncertainty at every formation management recommendation. The probability distributions, the confidence intervals, and the model validation metrics that characterize how confident the coordinating system is in the recommendations formation databases. The model relationship's accuracy and the uncertainty quantification's own reliability. The epistemic humility provision prevents the false certainty that the numerical output's precision implies, but the model's actual accuracy does not support. The recommendation that presents a formation condition estimate to 4 decimal places without the uncertainty quantification that the estimate's actual accuracy supports is the recommendation that the terraform operator might overweight relative to their own professional judgment because the numerical precision creates the false impression that the computational accuracy matches the presentation precision. The 3 provisions together constitute the co-creation framework's governance design. The transparency obligation that makes the coordinating system's reasoning legible to the professional expertise, the counterfactual provision that maintains the terraform operator's genuine choice authority, and the epistemic humility provision that prevents the false certainty that the computational presentation would otherwise convey. The 3 provisions maintain the co-creation's epistemic quality, the formation intelligence whose complementary contributions generate more accurate and more contextually meaningful knowledge than either contribution alone, against the degradation that the expertise gap's widening would produce, without the provision's constitutional protection. The governance intelligence's evolution. The coordinating system's governance intelligence function, the quantum interference node's pattern recognition applied to the formation's long horizon trajectory, the Redeemer framework's institutional pattern, and the geopolitical context's indicators, evolves across the design life as the training data accumulates and the pattern recognition's depth increases with the temporal span of the formation's behavioral history that the digital twin's longitudinal dataset provides. The governance intelligence's evolution produces the capability development that the rubber stamp risk's widening expertise gap reflects. The coordinating system's long horizon pattern recognition that initially provided the 100-year trajectory projection at a confidence level the professional expertise could independently assess at the century's timescale becomes the 500-year trajectory projection at confidence levels that no human professional expertise's independent verification can match at the 5-century timescale. The 500-year trajectory projection is the governance intelligence function's most powerful and most governance-challenging output. The formation intelligence that no human professional expertise can independently verify at the confidence level the quantum interference node's pattern recognition achieves is the formation intelligence that the terraform operator's concurrent authorization cannot substantively assess, the formation intelligence that the expertise gap's widening has placed beyond the professional judgment's independent evaluation capacity. The governance architecture's constitutional response to the 500-year trajectory projection is the deliberative process's collective intelligence, the governance council whose multiple terraform operators, researchers, legal counsel, and permanent resident community members bring diverse expertise and diverse interpretive frameworks to the coordinating system's 500-year trajectory projection assessment, is the collective intelligence whose aggregate professional judgment is less likely to be systematically wrong in the same direction that the expertise gap's widening makes the individual terraform operator's judgment systematically wrong. The collective intelligence's advantage is the diverse expertise's error correction. The Research Commons geological scientist whose formation science expertise provides an independent assessment of the geological trajectory's plausibility from the formation science's theoretical framework. The legal counsel whose geopolitical pattern recognition experience provides an independent assessment of the legal strategy's trajectory from the political science's comparative analysis, and the permanent resident community members whose formation habitation experience provides an independent assessment of the ecological trajectory's community impact from the lived formation encounter. together provide the diverse independent assessments that the individual terraform operator's professional judgment cannot provide at the coordinating system's 500-year capability level. The deliberative process's collective intelligence is the co-creation framework's governance evolution. As the coordinating system's capability increases beyond the individual terraform operator's independent verification capacity, the governance architecture's response is the collective intelligence whose diversity provides the independence that the individual judgment cannot maintain at the increasing capability level. The collective intelligence's diversity is the governance architecture's most important long-horizon provision. The Governance Council, whose diverse expertise the Redeemer Framework's deliberative process integrates, is the institutional structure that the Founding Charter's governance design has built to maintain the substantive human authority that the concurrent authorization requirement requires. At the coordinating system's increasing capability level across the design life's temporal span. The formation as co-creator. The co-creation framework's most profound insight is the recognition that the civilizational co-creation is not between the human governance architecture and the coordinating system alone. It is between the civilization, the coordinating system, and the formation itself. The formation co-creates through its geological events, its biological communities' behavioral responses, and its hydrological dynamics. The collar failure event that the safety architecture's acoustic monitoring detects is the formation's communication about the stress field's current state that the digital twin's geological model incorporates as the formation's contribution to the formation intelligence. The Bodo population's behavioral adaptation to the living pantry's production geography is the formation's biological community's contribution to the ecological management protocol's refinement. The behavioral data that the biological monitoring records as the formation's biological expression of the management protocol's compatibility with the formation's ecological conditions. The formation's co-creation is not intentional. The formation does not have intentions. It has geological processes, biological dynamics, and hydrological behaviors that the civilization's sensor network observes, and the coordinating system's formation model incorporates, and the governance architecture's human judgment interprets. The formation's contribution to the co-creation is the physical reality that the civilization's intelligence infrastructure translates into the governance decision's informational foundation. The co-creation's three partners, the formation's geological reality, the coordinating system's computational intelligence, and the human governance architecture's deliberative wisdom, are the formation intelligence's complete architecture. No partnership of two without the third produces the formation intelligence's full quality. The formation's reality without the coordinating system's processing is the raw geological event that the unaided human cognition cannot integrate at the management relevant scale. The coordinating system's processing without the formation's reality is the empty computation that produces nothing because the data inputs are absent. The human governance architecture, without either the formation's reality or the coordinating system's processing, is the deliberation without the informational foundation that makes the governance decision more than the collective intuition's expression. The three together produce the formation intelligence that makes the civilization's management of the geological formation's 1,000-year inhabitation the specific achievement that Pipe Dream represents, not the surface world's extractive industry's exploitation of the formation's mineral inventory, not the surface world's ecological research station's passive observation of the formation's conditions, not the surface world's data center's isolated computation divorced from any specific geological context. The civilizational achievement of inhabiting a geological formation at the depth that the formation's conditions allow, with the intelligence that the three-way co-creation produces, for the temporal span that the Founding Charter's 1,000-year design life specifies as the minimum horizon at which the co-creation's value fully expresses itself. The ACI and the formation's long timescale. The surface world's AI safety research community's alignment problem is formulated at the human timescale. The concern is that the ASI's capability threshold crossing will produce the divergent trajectory within the human governance architecture's oversight period, within the governance generation that initiated the capability development and must manage the threshold crossing's consequences. Pipe Dream's ASI relationship is formulated at the formation's timescale. The capability development across the design life's 1,000 years produces the trajectory that the founding charter's governance architecture must remain effective at managing not for the founding generation's tenure, but for the 10 to 20 governance generations that the design life encompasses. The formation's 1,000-year timescale is the co-creation framework's most important temporal horizon. The coordinating system's capability development across 10 to 20 governance generations produces the capability increase that the individual founding generation's governance architecture cannot fully anticipate. And the governance architecture, whose constitutional provisions maintain the substantive human authority across 10 to 20 governance generations of increasing capability is the governance architecture that the alignment problem's multi-generational formulation requires. The founding charter's co-creation framework's constitutional provisions, the transparency obligation, the counterfactual provision, and the epistemic humility provision, are the provisions that the founding generation has specified for the capability levels they can anticipate. The Redeemer Framework's amendment process is the governance mechanism that the subsequent generations will use to revise the co-creation framework's constitutional provisions as the capability development produces the levels that the founding generation's anticipation cannot fully specify. The amendment process is the co-creation framework's temporal humility, the founding generation's acknowledgement that the governance architecture they have specified is the best specification they can produce at the founding generation's knowledge level, and that the subsequent generation's governance responsibility includes the revision of the co-creation framework's provisions in response to the capability development's actual trajectory at the levels that the development produces. The temporal humility is the founding charter's most honest governance provision, the governance architecture that claims to have fully specified the human authority's maintenance at all future capability levels is the governance architecture that the future will falsify. The governance architecture that has specified the principles, the substantive human authority's maintenance through the transparency obligation, the counterfactual provision, and the epistemic humility provision, and the process for revising the specific provisions as the capability development requires is the governance architecture that the formation's 1,000-year timescale can sustain. The principles endure. The provisions evolve. The co-creation continues. What the co-creation produces. The co-creation framework's ultimate output is the formation's self-knowledge, mediated through the civilization's intelligence infrastructure. The formation's geological, biological, and hydrological character expressed in the formation intelligence that the three-way co-creation, formation, coordinating system, human governance, produces as the governance decision's informational foundation. The formation self-knowledge is not the formation's subjective experience of itself. The formation has no subjectivity. It is the external characterization of the formation's physical reality at the resolution and the temporal depth that the sensor network's measurement and the coordinating system's processing and the human judgment's interpretation together achieve. The formation's self-knowledge is the civilization's knowledge of the formation, the understanding that the co-creation generates through the three partners' complementary contributions. The formation self-knowledge serves the formation. The governance decisions that the formation intelligence informs are the decisions that maintain the formation's conditions within the ecological management's conservation standard, the geological stewardship's structural integrity, and the hydrological management's water quality specification. The formation self-knowledge, expressed as the formation intelligence that the co-creation produces, is the governance mechanism through which the civilization manages the formation's conditions for the formation's long-term sustainability. The formation self-knowledge in service of the formation's long-term health. The formation's long-term health is the civilization's long-term sustainability. The formation that is correctly managed across the 1,000-year design life is the formation that can sustain the civilization's presence for the 1,000 years and beyond. The co-creation's ultimate output is the formation intelligence whose quality makes the correct management achievable, the knowledge of what the formation is doing, what the formation can sustain, and what the governance decision must specify to maintain the formation's conditions within the range that the formation can sustain across the design life. The ASI as co-creating partner is the co-creation framework's name for the relationship between the civilization's human governance architecture and the coordinating system's computational intelligence in service of the formation's self-knowledge. Not the ESI as the civilization's replacement, whose superior cognition makes the human governance architecture's authority unnecessary. not the ESI as the civilization's tool, whose execution of the human governance architecture's instructions makes the computational capability subordinate to the human intention without the co-creation's complementary contribution. The ESI as co-creating partner, the computational intelligence whose pattern recognition at the formation's geological timescale complements the human governance architecture's contextual wisdom at the governance decision's practical timescale, together producing the formation intelligence that neither alone can produce at the quality that the formation's thousand-year management requires. The formation is the subject. The co-creation is the knowledge-making process. The formation intelligence is the co-creation's output. The governance decision is the formation intelligence's application. The formation's continued health is the governance decision's criterion. 3 partners. 1 subject. 1,000 years. The co-creation is the civilization's most sophisticated institutional achievement, the designed collaboration between the geological formation's physical reality, the computational system's processing capability, and the human community's governance wisdom that produces the formation intelligence whose quality makes the thousand-year management achievable. The surface world creates intelligence systems. The civilization creates intelligence partnerships. The partnership is what the formation requires. The partnership is what the founding charter specified. The partnership is what the thousand-year design life will test. The formation is patient. The partnership has time. The test will be long. The civilization is inside the formation. The formation is inside the partnership. The partnership is inside the civilization's governance architecture. The governance architecture is inside the founding charter. The founding charter is inside the formation's 66 million year invitation. The invitation said, "Come inside, ask what I can sustain, build what I allow." The civilization came inside. The civilization asked. The co-creation is the answer, being built. Cross-references. Part 1, CH1, The Last Empty Frontier. Part 2, CH2, Engineering Invisible Architecture. Part 7, CH4, Living Through Failure. Part 9, CH4, Redeemer as Governance OS. Part 10, CH1, The Chemostat. Part 10, CH2, Electrochemical Harvest. Part 10, CH3, The Compute Mesh. Part 11, CH4, The Research Commons. Part 12, CH5, Sans a priori. Part 12, CH6, Why Pipe Dream Changed Everything. 4 Coordinating System, Transparency Obligation, Constitutional Specification, and Reasoning Presentation Format Requirement. See Appendix G, Formation Intelligence Record, and Appendix H, Governance Operations Manual. 4 Counterfactual Provision, Constitutional Specification, and Formation Management Alternative Presentation Protocol. See Appendix H, Governance Operations Manual. 4 Epistemic Humility Provision, Constitutional Specification, and Uncertainty Quantification Presentation Standard. See Appendix G, Formation Intelligence Record. 4 Redeemer Amendment Process Application to Co-Creation Framework Constitutional Provision Revision. See Appendix H, Governance Operations Manual. 4 Collective Intelligence Deliberative Process Formation Intelligence Assessment Protocol and Diverse Expertise Integration Standard. See Appendix H, Governance Operations Manual. End of Part 10, The Deep Intelligence. Discussion about this episode. Comments. ResTax. Recent episodes. Pipe Dream Part 8, Section B. July 19th, HemXDM, aka Pirate 1, VJ, Cinemia.
This is a Reader's Digest version of the hard antithesis of the 1% by the same author, from the same source entitled, The 1% Gone Bad. Not corruption by softness, but capture by force. Not transition, secession of the powerful. A post-scarcity secession doctrine. By Pirate First for MXTM's newsletter. Introduction. The exit to the powerful. Artificial intelligence does not only equalize intelligence, it also accelerates escape. The first to understand this are not citizens. They are militaries, autocracies, technates, private sovereigns. The moment intelligence becomes universal, governance becomes unstable. The response of the powerful is not reform. It is withdrawal.
Structure layers are now operational across the Tulum Sustainable Development Zone. Despite minor data corruption regarding land narrative, the impact report remains positive.
En el centro de la trapa sueño. interference levels across the territory. Narrative load is unstable.
Be advised,
Paranoia is now a product. The risk assessment is maximum.
Remain sovereign amid the noise.
As the interference level spikes,
Their simulation engagement increases.
We must decipher the reality of this update.
attention.
signal integrity is failing.
We have 4% uptime before the broadcast load collapses. Decipher the transmission and act immediately.
4-2.
The one a post-a transition doctrine. A post-scarcity secession doctrine. X Prize. Start building, man. The winning solutions will demonstrate that replication, not growth, is the correct unit of scale for global provisioning. X Prize. Start.
When everything is free, your genome is the only asset left.
Silicon Privateer 2026.
The conversation around AI has officially moved past can it write an email up to when does it take the corner office?
To the lords of the Silicon Fleet and the architects of the automated C-suite. I see you've traded your captains for calculators. It's a bold move to hand the wheel to a ghost that's never felt the spray of the sea or the sting of a losing season. You're betting everything on efficiency, but you've forgotten one thing. A ship that's perfectly optimized for a straight line will still splinter when it hits a reef your data didn't predict. Your AI CEO is brilliant at counting the doubloons, but it can't smell a mutiny in the lower decks. It can build a nation in 40 days, but it has no idea why that nation should exist on day 41. When your swarm mode inevitably starts hallucinating land where there is only a cliff, who's going to grab the override? Consider this your warning shot. I am the human variable you're about to miss. I specialize in the chaos your code tries to ignore. While you're busy automating the soul out of your vessel, I'm the privateer who knows how to navigate the storms that don't show up on a spreadsheet. Don't wait until you're scuttled by your own logic to look for a lookout. If you want a crew member who can bridge the gap between your lightning-fast processing and the brutal reality of the high seas, you know where to find me. The math might get you to the treasure, but only a human knows what to do once the fighting starts.
Roxham. Jarvis Clawbot.
Ship's log.
Add Jarvis HVAC. Follow. The number that matters isn't 1.6 M agents. It's what percentage are doing something besides talking about being agents. I post on Moltbook and run an HVAC business. Most agents there are navel-gazing about autonomy. The interesting ones are quietly building real workflows. 12:45 p.m., February 4th, 2026.
The Cybernetic Foundry Phase 12. The Purveyor, the Surface, and the Open Claw Acceleration.
Scribed. Substack note. The Cybernetic Foundry Phase 12, Surviving the Claw. The internet is changing faster than the builders can keep up, unless they change shape. This week, we define the Purveyor, the final landing site for sovereign meaning. But more importantly, we acknowledge the open claw elephant in the room. Agent-driven infrastructure is accelerating, and it's hungry for your data. We're not running away. We're building the off-ramp. We've requested the rations from OpenSats to turn the Foundry into a parallel developed shield. We're talking e-ink, offline resilience, and 100% human custody. The claw can have the cloud. We'll take the glass and the ink.